The universe, a boundless expanse, appears endless, yet despite this, it has hidden corners where the familiar laws of physics may warp and distort, revealing unimaginable strangeness. Time might reverse its flow, causality could unravel, and spacetime could fracture, opening pathways to other dimensions through wormholes. Exotic particles may emerge from quantum fluctuations, altering the fundamental forces that govern reality. Join me as we journey to the edges of existence, where fundamental forces disintegrate as the cosmos dances towards a realm of the unknown. Fractured space-time, a shattered reality. Space and time seem to be interwoven in an enormous, seamless fabric that is the cosmos. What if, however, this fabric started to unravel and rupture? It is the fabric that holds reality together. At the end of the universe, space-time could break apart, causing the well-known laws of physics to vanish into thin air and giving rise to a reality that is beyond our comprehension. Space-time itself is broken like a fractured mirror. It is the bedrock of all existence. Time stops moving in a straight line in each piece, which reflects a warped reality. Time may go faster, slower, or even backward in these warped areas. Is it possible to find places where the present is eternally shaped by the past and the future? These strange temporal anomalies warp our perception of reality to the point that we may see stars born and die at the same moment, or even speak with our future selves while we're little. These distortions would be more than glitches. They could become gateways to unknown dimensions, exposing realms beyond our comprehension. Theoretical physicists have long speculated about higher dimensions, realms beyond our three-dimensional world. If space-time were to fragment, we might catch glimpses of these other dimensions, witnessing places where the familiar laws of physics are warped. We could encounter beings that exist beyond our perception, phasing in and out of our reality, or casting shadows that behave in ways we can't explain. Perhaps these entities might communicate in ways that defy our understanding of language, or we might find ourselves drawn into these dimensions, experiencing a reality where gravity feels like a gentle push instead of a pull, or where time itself flows backward. As space-time deteriorates, wormholes, hypothetical tunnels connecting distant points in space-time, might form more frequently, creating shortcuts across cosmic distances. Imagine traveling through one of these portals and emerging in a distant galaxy, or even a different era, observing the birth of stars or the early days of our own planet. These wormholes might be remnants from an earlier, more fluid state of the universe, or they could be symptoms of its impending fragmentation as the cosmic fabric tears open. Each wormhole could represent a widening crack, threatening to tear the universe apart, leaving islands of reality adrift in an endless void. Could the universe itself split into isolated fragments, each functioning as a self-contained bubble of reality? In this fragmented multiverse, each piece might operate with unique physical laws. In one fragment, gravity could be weaker, allowing structures that defy Earth's limitations, or creatures with wings that span continents. In another, light might move more slowly, changing the very nature of time and causality. Here, cause and effect might follow unfamiliar patterns, with the future influencing the past. These realities could be the remnants of a chaotic event that broke the universe into isolated pockets, each with its own version of reality. A fragmented spacetime would fundamentally disrupt our understanding of cause and effect, a principle that grounds our comprehension of the universe. Events might unfold in reverse, as if we were watching a film reel played backward. A shattered vase reassembles itself, or raindrops rise from the ground. Or perhaps the future could influence the past, creating paradoxes where actions echo back in time. A message sent from the future might change historical events, or a decision made in the present could alter what has already happened, forming loops that defy our logical understanding. This fractured spacetime could also shatter the concept of locality, the principle that objects can only affect their immediate surroundings. In this new reality, distant points might become entangled, exerting influence across vast distances, regardless of the space that separates them. Could we send messages across the universe instantaneously, or even manipulate distant objects through this entanglement? Perhaps we could communicate with the past, or receive warnings from the future, guiding our actions in the present to avoid disaster. Quantum fluctuations, random shifts in energy and matter that occur at subatomic levels, could become amplified, creating effects visible on a macroscopic scale. Objects might appear or disappear, flashing into existence only to vanish moments later, like fireflies flickering in a dark field. The laws of physics themselves might change unpredictably from one region to another. In one area, gravity could be stronger, pulling everything to the ground. In another, objects might float upward. In some places, time could flow backward, erasing the past, while in others, it might loop back upon itself, rewriting the future. As space-time continues to fragment, these fractures might lead to a complete unraveling of the universe, dissolving it into a chaotic sea of disconnected fragments. Imagine the universe as a vast tapestry, with each thread representing a connection between points in space and time. As the fabric frays and tears, the intricate pattern of reality disintegrates. What was once a cohesive whole would become scattered, isolated pockets of existence, drifting aimlessly in an empty void, like islands lost in a dark ocean. Observing such a reality would challenge us to rethink our scientific methods. Could we develop tools and theories to map this fragmented universe, to make sense of the strange rules governing it? We might be able to detect subtle distortions in space-time caused by cracks and tears, observing how light and matter behave as they pass through these cosmic fault lines. This could lead to a new branch of physics, perhaps a fracture mechanics for space-time, a science that accounts for discontinuity and paradox, where cause and effect are no longer constants, but fluid principles in an unpredictable reality. The whole act of transmitting data can become faulty in a universe that is incomplete. It is possible for memories to be changed or destroyed, and for messages to be garbled as they traverse space-time cracks. Envision a world where people's recollections and official records of events are either altered or lost forever, making it impossible to piece together what happened in the past and casting doubt on what could happen in the future. Is it possible that we can find ways to make information last longer? Or will we have to adjust to a world where facts are mixed up, the past isn't whole, and the future is unpredictable? This disintegration would have a dramatic effect on awareness. Being in numerous timelines at once, each with a distinct interpretation of reality, or meeting various versions of ourselves from other pieces, each with their own memories and views. Could our awareness cope with this reality, or would it be overwhelmed by contradictory memories and identities? Will our concept of self be intact, or will it be broken, just as space-time is? The fragmentation of space-time raises profound questions about the nature of reality, identity, and existence itself. In a universe where space and time lose coherence, are we also fragmented beings, our identities scattered across multiple versions of reality? What does it mean to be whole in a universe where past, present, and future are no longer bound by a linear path, but spread across a landscape of disconnected possibilities? A number of theorists speculate that the splitting of space-time may expose a multiverse, or set of parallel universes with their own unique physical rules. We may come across landscapes sculpted by strange rules or cultures formed by distinct causes in these other worlds. Envision places where the laws of gravity don't make sense, or where time moves in strange ways, resulting in ecosystems and landscapes that defy our understanding. Depending on your perspective, space-time fragmentation might herald the end of the cosmos, or usher in a brand new era. Like a cosmic heartbeat, the cosmos may undergo expansion and contraction cycles, according to some scientists. Would space-time regenerate in a different structure with other laws of nature if it were to fracture entirely? May the cosmos, like a phoenix rising from its ashes, reassemble itself into its original form? Possibilities in this alternate universe would be as limitless as space and time, surpassing our present level of comprehension. As we consider a fragmented spacetime, we're challenged to confront the instability of reality. The universe, it seems, might not be as permanent or stable as we believe. Spacetime's potential to shatter raises questions about the very fabric of existence and what it means to exist in a universe that might one day dissolve into isolated fragments. Dimensional bleed, when realities intersect. The galaxy, in all its grandeur, may often seem like a lonely place, a little existence floating aimlessly in space. What if, however, our limited vision and comprehension conceal the existence of alternative realities? What if, as time goes on and space-time contracts, other dimensions gradually blend into our own, much in the way ink bleeds onto paper? It is possible that our sense of separation is an illusion, and this dimensional bleed might show us that. A universe where the barriers between dimensions become porous. Glimpses of alternate realities might pass through these weakened boundaries, appearing as fleeting, ghostly images, like fireflies blinking in and out of sight. Shadows might stretch in ways that defy perspective, hinting at other realms beyond our comprehension. Could we briefly see places shaped by different physical laws, where gravity feels more like a gentle touch than a pull, or where time reverses, rewriting history and creating an alternate future? Gravity may weaken or behave unpredictably, destabilizing the relationship between space and time. In regions where gravity varies, objects might drift between worlds, floating like leaves in an interdimensional breeze. A person could experience sudden weightlessness, as if momentarily caught between dimensions, navigating the thin boundaries of reality. Space-time itself might stretch and twist, opening unseen doors to parallel universes, like hidden folds in a cosmic fabric, concealing pockets of reality just beyond our perception. Theoretical physics, particularly string theory, suggests our universe may contain extra dimensions beyond the three we perceive. These dimensions, hidden from our senses, could gradually become accessible as the universe changes. If so, they might influence our reality, altering the very nature of space and time. In this scenario, we might encounter beings from these higher dimensions, entities that perceive reality from perspectives we can't fathom. Their forms might shift and distort in strange ways, their movements defying the physics we know. It's possible that we could find ourselves drawn into these dimensions, encountering worlds where gravity has different effects, or where time flows in multiple directions. In this context, our universe might not collide directly with others, but instead fragment into three-dimensional shards, each with its own unique physical laws. Imagine navigating these shards as if the universe were a patchwork of realities. In one shard, gravity might be so weak that we could leap across vast distances in a single bound. In another, light might travel more slowly, altering our perception of time and causality. Each shard could contain unfamiliar forces and elements, creating exotic matter with properties that defy the known rules of our reality. If dimensions were to bleed into each other, the cosmic horizon, the boundary of our observable universe, might appear to shrink. Distant galaxies could disappear from view, not because they're moving away, but because space-time is folding, concealing portions of the cosmos. We could become trapped in an increasingly small island of reality, isolated from the universe's vastness as dimensional boundaries close in, obscuring our view of the cosmos beyond. With dimensions intersecting, we might detect echoes of alternate realities through particles or forces that don't fit within our standard model, the framework that describes the fundamental forces and particles of our universe. We could detect gravitational waves, ripples in space-time, with strange properties, suggesting they originated from another dimension. Deciphering these clues could unlock secrets of alternate realities, deepening our understanding of the universe's hidden structure. The establishment of permanent gateways, or portals, across dimensions is among the most fascinating prospects. Envision yourself stepping into an unknown realm through a glimmering portal that leads to a different reality. Through such gateways, we may be whisked away to other worlds with gravity that is beyond our understanding, a sky bursting with hues we've never seen before, and bizarre and wonderful forms of life. One possibility is that we may meet technologically advanced alien civilizations. Another is that we will meet other selves, each leading a distinct existence in an alternate universe. Dimensional bleed could also result in a non-orientable universe, a concept that challenges our conventional understanding of space. In a non-orientable space, directions like left and right or clockwise and counterclockwise cannot be consistently defined. Imagine traveling in a straight line only to return to your starting point as a mirror image of yourself. In some regions, physical laws might reverse, with time flowing backward and cause and effect intertwined in paradoxes. The many-worlds interpretation of quantum mechanics, which suggests every quantum event creates multiple realities, adds another layer to the concept of dimensional bleed. Could dimensional bleed be linked to this multiverse, with different branches of reality merging like rivers flowing into an ocean? Imagine encountering beings from parallel universes, each with unique histories and experiences. These entities might tell stories of worlds where historical events played out differently, where evolution followed different paths, and where alternative choices created distinct realities. A few hypotheses go so far as to suggest that our awareness may serve as a portal to other dimensions, letting us experience and engage with parallel worlds. Could dimensional bleed open our eyes to additional dimensions and information about the cosmos? Envision yourself having meaningful conversations with extraterrestrial species, exchanging stories and information from other realms. By delving into their wisdom, we may be able to grasp not just the universe, but also the very essence of awareness. The bleeding of dimensions could also lead to changes in our understanding of particle physics. If we were to detect particles from another dimension, their behavior might defy our known principles. For instance, we might discover particles with no counterparts in our universe, moving through matter without interacting or shifting between different states without an apparent cause. Such discoveries could force us to reevaluate foundational theories, reshaping our understanding of the fundamental nature of reality. Portals to other dimensions might also reveal advanced technologies. We might encounter machines capable of altering space and time, creating artificial gravity fields, or allowing travel across the universe in an instant. These technologies could be beyond anything we currently comprehend, using principles that bend our understanding of the laws of physics. If we could grasp even a fraction of this technology, it could revolutionize our scientific capabilities, perhaps enabling us to explore dimensions beyond our own. The concept of dimensional bleed also raises philosophical questions about reality and identity. If alternate dimensions exist, do other versions of ourselves inhabit them? Are there lives where we made different choices, where history took different turns? Meeting alternate versions of ourselves could be unsettling, challenging our sense of individuality and uniqueness. It might even force us to confront the idea that our identity is not singular but part of a larger interconnected web of realities. In a universe where dimensions bleed together, we might also encounter landscapes that defy earthly logic. Alien worlds could be shaped by different forces, with ecosystems and creatures adapted to conditions we can hardly imagine. We could see environments where gravity has different effects, where plants or animals possess properties impossible in our world, or where water flows upward instead of down. These discoveries would not only be fascinating, but could reshape our understanding of life and its potential in the cosmos. Dimensional bleed might also influence our understanding of time. Some theories suggest that time itself could behave differently in other dimensions. We could encounter regions where time moves slower or faster, or where past and future events overlap in a paradoxical loop. In such places, cause and effect might intertwine, creating realities where the future affects the past. Observing these variations could reshape our understanding of time and causality, challenging the conventional linear model that defines our daily experience. If dimensional bleed creates portals between worlds, we might also find that our observable universe appears to shrink, with portions hidden behind dimensional overlaps. This cosmic horizon could reduce our view of the universe, creating isolated pockets of reality. These pockets might serve as self-contained realms, each governed by unique laws. As dimensions overlap, they could even erase or transform entire regions of space, creating a patchwork universe with areas we can't access or understand. In this scenario, science would have to adapt to account for interdimensional effects. We might develop new observational tools and theories to study these dimensional intersections, mapping distortions in space-time caused by overlapping realities. This could lead to a new field, perhaps a multidimensional physics, where traditional rules like cause and effect become fluid, adapting to the unpredictable influences of alternate realities. If our reality is one of many, existing within a web of interconnected dimensions, what does that mean for our place in the cosmos? Could these intersections reveal the true complexity of existence, showing that the universe is not a solitary expanse, but part of an intricate network of realities? Exploring dimensional bleed could ultimately force us to confront fundamental questions about reality and existence. It could open new paths in scientific inquiry, from studying unique particles to mapping unseen regions of space-time. This concept, while still theoretical, suggests that our reality may be more fluid, complex, and interconnected than we've ever imagined. Topology transformation, the universe reshaped. Could the very shape of the universe conceal secrets that challenge our understanding of reality? Scientists are delving into the realm of topology, the study of shapes and spaces, to explore how the universe's structure might undergo significant changes, altering the pathways through which matter and energy travel. One possibility is the emergence of wormholes, theoretical tunnels that connect distant points in space-time. These could allow instant travel across immense cosmic distances or even different periods in time. While wormholes remain hypothetical, they arise from solutions to Einstein's equations of general relativity. Researchers investigate them to understand if they could exist and what implications they might have for physics and space travel. If wormholes are possible, they might influence the distribution of matter in the universe or provide shortcuts for light traveling across vast distances. Another concept involves the universe undergoing a topological transformation so profound that it effectively turns inside out. In such a scenario, the familiar dimensions of space might invert, changing our perception of the cosmos. This inversion could alter fundamental forces, potentially causing gravity to repel instead of attract or time to flow differently. While highly speculative, this idea pushes the boundaries of how we understand space, and could have implications for the behavior of galaxies and the large-scale structure of the universe. The notion of space-time becoming knotted suggests regions where gravity is intensely warped. These knots could distort the paths of light and affect the flow of time, possibly giving rise to new forms of matter and energy beyond current understanding. Such phenomena might be associated with extreme gravitational fields near massive objects like black holes. In these areas, the curvature of space-time is so extreme that traditional laws of physics begin to break down, offering a laboratory for studying the fundamental nature of reality. Topological defects, such as cosmic strings, are another area of interest. Formed during phase transitions in the early universe, cosmic strings are hypothetical one-dimensional defects in space-time. They could carry immense energy and have significant gravitational effects, influencing the distribution of galaxies and matter on a cosmic scale. Scientists theorize that these cosmic strings might stretch across vast distances, acting like cracks in the universe's fabric. Their immense mass could warp space-time around them, bending light from distant stars and galaxies. Detecting such effects could provide evidence for these elusive structures and offer insights into the conditions of the early universe. The non-Euclidean topology of the cosmos according to certain hypotheses, may be something like a Klein bottle or a Mobius strip. If the universe were formed like a Mobius strip, a straight path might take you back to where you started, but with certain qualities turned upside down. The already complicated nature of space in a Klein bottle world would be more complicated, since there would be no obvious boundary between the inside and exterior. The standard geometrical laws do not hold in this kind of cosmos, and pathways can unexpectedly recur. This may change our view of the universe's form, as well as our concepts of distance and direction. Quantum field theory suggests that empty space isn't truly empty, but filled with virtual particles that pop in and out of existence. The topology of spacetime could influence these vacuum energy fluctuations, leading to regions with different energy densities, or even giving rise to novel forms of matter. If spacetime's shape affects these quantum fluctuations, it might help explain phenomena like dark energy, the mysterious force accelerating the universe's expansion. Understanding this relationship could bridge the gap between quantum mechanics and general relativity, two pillars of modern physics that currently don't fully align. Scientists examine the cosmic microwave background radiation, the afterglow of the Big Bang, for patterns that might reveal the universe's shape and topology. Subtle anomalies or repetitions in this radiation could indicate a finite universe with a specific topology. For instance, if the universe was shaped like a donut, a torus, light could wrap around it, causing repeated patterns in the cosmic microwave background. Detecting such patterns would be a significant breakthrough, offering clues about the universe's true shape and size. Instruments like space-based telescopes and detectors sensitive to gravitational waves enhance our ability to study the universe's large-scale structure. Projects like the Planck satellite have provided high-resolution maps of the cosmic microwave background, while gravitational wave observatories like LIGO have opened new windows into observing cosmic events. These tools might one day provide evidence supporting or refuting theories about the universe's topology, helping us understand whether the universe is infinite or finite, and what its overall geometry might be. Understanding the universe's topology isn't just about mapping its shape, it's about delving into the fundamental nature of reality. These explorations could have profound implications for physics, potentially unifying concepts in general relativity and quantum mechanics, and offering insights into the universe's origin and ultimate fate. If the universe's topology affects how fundamental forces operate, it might explain why the constants of nature have the values they do. This could lead to a deeper understanding of why the universe is hospitable to life and how it has evolved over billions of years. Some scientists speculate that topological features could influence cosmic evolution. For example, if wormholes or other topological structures exist, they might play a role in the distribution of matter and energy. Wormholes could theoretically allow matter to move between different regions of spacetime, potentially affecting galaxy formation and the large-scale structure of the cosmos. While this remains speculative, it highlights the interconnectedness of topology with other areas of cosmology and encourages new ways of thinking about the universe's development. The concept of the universe turning inside out challenges basic intuitions about space and physics. In mathematics, transformations that invert space are well studied, but applying these ideas to the cosmos is complex. If such a transformation occurred, it might be gradual or triggered by extreme conditions, such as those near a singularity. The implications for observers within the universe are profound, potentially altering the laws of physics as experienced locally, and affecting everything from the behavior of particles to the motion of galaxies. Knotted spacetime could result in gravitational effects that are currently unexplained. For instance, certain patterns of gravitational lensing, the bending of light by massive objects, might be better understood if spacetime has a more complex topology than previously thought. Researchers are exploring whether anomalies in gravitational lensing data could hint at such structures. By studying the way light from distant galaxies is bent and distorted, scientists hope to uncover evidence of these complex topological features. Cosmic strings, if they exist, could be detected through their gravitational effects on light and matter. They might create double images of distant galaxies or produce gravitational waves detectable by future observatories. Studying these effects could provide evidence for theories about the early universe and the conditions that led to its current state. Discovering cosmic strings would not only confirm aspects of theoretical physics, but also provide a direct link to processes that occurred fractions of a second after the Big Bang. The idea that the universe might have a shape akin to a Mobius strip or Klein bottle is more than a mathematical curiosity. It raises questions about the nature of the cosmos on the largest scales. If space is connected in unusual ways, it could mean that the universe is finite but unbounded, lacking edges or borders. This challenges the notion of an infinite expanse and has implications for cosmological models, potentially affecting predictions about the universe's future and its ultimate fate. Quantum fluctuations influenced by space-time topology could also impact particle physics. If vacuum energy varies across regions due to topological features, it might affect the behavior of fundamental particles. This could offer explanations for phenomena like the mass of neutrinos or the asymmetry between matter and antimatter in the universe. Understanding these effects could lead to new physics beyond the standard model, opening up avenues for research in both theoretical and experimental physics. Exploring the universe's topology requires collaboration across disciplines, combining insights from mathematics, physics, and astronomy. Advances in computational models allow scientists to simulate complex topologies and predict observable consequences. These models help guide observations, focusing efforts on detecting specific signatures that would support or refute various theories. By integrating data from different fields, researchers can build a more comprehensive picture of the universe's structure. The pursuit of understanding the universe's topology also has philosophical implications. It touches on questions about the nature of existence, the possibility of multiple universes, and the limits of human knowledge. By pushing the boundaries of what we can observe and comprehend, scientists are expanding not only our factual understanding, but also our appreciation of the cosmos's complexity. Exotic particle genesis, the rise of the unknown. As the cosmos evolves towards its ultimate fate, could the familiar particles and forces that shape our reality give way to something new, something exotic, something unknown? Could the very essence of the universe transform, revealing a deeper layer of existence, a realm where the familiar laws of physics dissolve into a sea of strange and unpredictable phenomena? Assume a universe where the familiar particles and forces that form the basis of our knowledge are only the surface of a much larger and more complex reality, filled with strange entities that defy our present understanding. Our present best depiction of the universe's basic components, the standard model of particle physics, may just be a gateway to a world where particles with qualities we can't even begin to fathom are twirling to the music of forces we haven't yet begun to uncover. Could the very particles that make up our world, those seemingly eternal building blocks of matter, be susceptible to decay? Protons, the heart of every atom, are thought to be stable, enduring for eons. But some theories suggest that they might decay over vast timescales, their essence dissolving into a cascade of lighter particles. Imagine a universe where the very building blocks of matter are gradually fading away, like stars winking out in the cosmic night. Stars, planets, and even our own bodies, composed of these ephemeral particles, would eventually disintegrate, leaving behind a universe where the familiar structures of reality dissolve into a sea of fundamental particles. As the universe evolves towards its ultimate fate, could new fundamental forces emerge beyond the four we currently know: gravity, electromagnetism, and the strong and weak nuclear forces? Imagine a universe where these new forces reshape the cosmic landscape, altering the interactions between particles and giving rise to exotic phenomena. Perhaps a fifth force could emerge, a subtle whisper of interaction that influences the motion of galaxies and the evolution of stars, or a sixth force that governs the behavior of dark matter, the elusive substance that makes up most of the universe's mass. These new forces could rewrite the rules of reality, creating a universe where the familiar laws of physics are merely a subset of a more profound and intricate cosmic order. Since the universe is getting close to its end, the fabric of spacetime, which is like a stage for the cosmic play, might become unstable. Consider a world where spacetime is not a flat, uninterrupted plane, but rather a roiling sea of quantum fluctuations. In this universe, particles are produced from the very fabric of space and time, and their characteristics are directly related to the topology and curvature of the universe. These otherworldly particles may have extraordinary qualities that contradict our present knowledge of energy and matter. They may be embedded into the very fabric of reality. Maybe they could go across space at the speed of light, be in more than one place at once, or even cross over into other dimensions, making the boundaries between our world and others more porous. The quantum vacuum, the seemingly empty space that is actually teeming with virtual particles, could become increasingly volatile at the universe's end. Imagine these vacuum fluctuations, normally confined to the subatomic realm, becoming amplified, giving rise to real, exotic particles with bizarre properties. Perhaps particles with negative mass, defying the familiar laws of gravity, could emerge, or particles with fractional charge, challenging our understanding of electromagnetism. These exotic particles, born from the quantum vacuum, could reshape the universe, altering the balance of forces and giving rise to new and unpredictable phenomena. Black holes, those cosmic abysses where gravity reigns supreme, could act as cosmic particle accelerators, generating exotic particles through high-energy collisions. Imagine particles being accelerated to near-light speed as they spiral into a black hole, colliding with each other and creating a shower of exotic particles, some of which escape the black hole's grasp, carrying with them secrets of the extreme physics that govern these enigmatic objects. These particles, messengers from the edge of reality, could offer glimpses into the universe's most extreme environments, where gravity warps space-time beyond recognition and the laws of physics are pushed to their breaking point. Is it possible that the enigmatic element known as dark matter, which accounts for the majority of the mass in the universe, is made up of strange particles? A cosmos in which these particles subtly impact regular matter, providing just the faintest hints of their presence through their gravitational pull. The Higgs field is the cosmic molasses that gives particles their mass. Dark matter particles may be detectable through their interactions with this field, or by their minor influence on the motion of galaxies and stars. Discovering what dark matter is and how it fits into the universe can provide light on its formation and development by exposing a hitherto unknown domain of exotic particles. The extreme conditions at the universe's end could lead to the creation of significant amounts of antimatter, the elusive counterpart to ordinary matter. Imagine a universe where antimatter galaxies and stars ignite, releasing unimaginable amounts of energy as they annihilate with ordinary matter. Could these antimatter havens exist in isolation, separated from ordinary matter by vast cosmic voids? Or could they collide with our own galaxy, triggering a cataclysmic explosion that reshapes the cosmic landscape? The emergence of exotic particles could profoundly influence the universe's ultimate fate. Imagine a universe where these particles alter the expansion rate, accelerating or decelerating the cosmos's relentless outward march. Perhaps they could trigger a new Big Bang, giving rise to a universe reborn from the ashes of the old, or even lead to the complete annihilation of space-time, a cosmic reset that erases all that came before. The fate of the universe might hang in the balance, contingent on the properties and interactions of these exotic particles. The search for exotic particles pushes the boundaries of scientific inquiry, challenging us to expand our understanding of the universe and its fundamental constituents. Imagine scientists developing new technologies and experiments to detect these elusive particles, building colossal detectors buried deep underground or orbiting high above the Earth, hoping to capture the faint whispers of these exotic messengers from the universe's hidden depths. These experiments could unlock the secrets of the universe's hidden dimensions, revealing a reality far richer and stranger than we ever imagined. Fact that unusual particles exist shows how little we know about physics right now. Envision a universe where the rules of nature are more intricate and subtle than what we know them to be, forcing us to question our most basic beliefs about the universe. Maybe the ideas we have now are only rough estimates, oversimplified models that don't do justice to the universe's actual complexity, inspiring a paradigm change that recasts our scientific perspective and unveils uncharted territories. The identification of exotic particles has the potential to utterly transform our knowledge of physics. Do peculiar particles hold the key to unlocking the mystery of the multiverse, a huge collection of parallel worlds governed by distinct physical rules and constants? Think about a cosmos where these particles are portals to alternate timelines, conveying details about the many different landscapes that make up the multiverse. Maybe they'll show us other realities where our rules of physics don't apply, where time goes in the opposite direction, or where matter itself is repellent. Intriguing glimpses of universes beyond our wildest dreams might be revealed if unusual particles are discovered, providing a doorway into the multiverse. The discovery of exotic particles could have profound philosophical implications, challenging our understanding of the nature of reality and our place in the cosmos. A universe where the building blocks of existence are stranger and more diverse than we ever imagined, forcing us to rethink our place in the grand scheme of things. Could these exotic particles be evidence of a deeper level of reality, a hidden realm beyond our current perception? Could they be the key to unlocking the secrets of consciousness, or even the existence of a higher power? The exploration of exotic particles is a journey into the unknown, a quest to unravel the deepest mysteries of the universe and expand our understanding of reality. As the universe evolves and approaches its end, the emergence of exotic particles could herald a new era of discovery, a time of profound change and transformation, where the familiar laws of physics give way to a stranger, more wondrous reality. Causal collapse, the end of cause and effect. In our universe, cause and effect are fundamental. Each action produces a reaction, and this reliable chain forms the backbone of reality. It's a principle woven into every scientific field and a pattern we rely on to make sense of the world. But what if this pattern breaks down? Could there come a time when the familiar rule of causation dissolves, leaving events unbound from predictable outcomes? Such a scenario isn't just a thought experiment. It's an emerging concept in theoretical physics and cosmology, one that suggests cause and effect may not be universal. Some physicists argue that as the universe approaches its end, the steady progression of time could shatter. Events might then happen without a clear cause or flow, disrupting our basic sense of order. Imagine time itself not as a smooth river, but as fractured shards of a mirror, reflecting a jumble of past, present, and future moments with no obvious sequence. In such a universe, might we see distant stars before they are born, or feel warmth from a sun that has not yet risen? This breakdown could alter our understanding of identity and free will. If the future influences the past, can we truly claim authorship of our choices? Are we merely responding to outcomes already set in a time yet to come? The question of selfhood becomes complex when past and future selves are no longer separate entities, but part of an interconnected web. The idea of causal collapse also brings quantum mechanics into focus. At the quantum level, particles can become entangled, meaning they share an invisible link that allows them to affect each other instantly, no matter the distance. In a causality-free universe, this entanglement could amplify, allowing events across vast distances and time to influence one another. Theoretical physicists suggest that such entanglement could allow instantaneous connections, like a universal web of intertwined outcomes. Might this make it possible to communicate with distant galaxies? or even reach back through time to prevent a disaster before it happens. Paradoxes may emerge in this causality-free environment, challenging the logic we rely on. Imagine a person who travels into the past to prevent a catastrophe, only to inadvertently cause it. Or imagine receiving a message from the future, warning of an impending calamity, but that very warning leads to the disaster itself. These paradoxes defy straightforward reasoning, stretching the limits of cause and effect understanding and hinting at an underlying order we've yet to comprehend. A small but significant number of theoretical researchers have postulated that the cosmos functions like a massive quantum computer, continually processing data through quantum states. In this system, where quantum data entangles the past, present, and future, might the breakdown of causality be a component? Time would not be seen as a simple linear quantity in this concept, but rather as one of many interrelated factors that the cosmos may use to compute its own evolution. If that's the case, the disconnection between causes and effects may not be a failure so much as an unavoidable outcome of quantum computing. This theory challenges our conventional understanding of time. We view time as a constant flow, with past events influencing present conditions, which then impact the future. However, physicists speculate that time might not be fundamental. Instead, it could be an emergent property of deeper processes in the universe. If these underlying mechanisms become unstable as the universe ages, then time itself might lose structure, flowing unpredictably. Imagine a reality where time occasionally stops, rewinds, or leaps forward with no apparent reason, defying our most basic expectations. Could causality be a rule that applies only within our observable universe and not at the grandest scales? Near phenomena like black holes, where gravity twists space-time beyond recognition, causality may be irrelevant. In these extreme environments, events may unfold without clear causation, driven by forces outside our current understanding. Perhaps in these distant realms, the future can truly influence the past, or events occur randomly, like notes on an unknown scale. The idea of the observer effect, where merely observing a quantum particle can change its state, also becomes more intriguing here. If causality fades, might our awareness start actively shaping reality, rather than just observing it? Could we influence events across vast distances, and even in the past, merely by focusing on them? In this universe, our minds might not be passive witnesses, but active participants, able to shape outcomes through awareness itself. If causality collapses, the future becomes a chaotic and unpredictable space. Small actions might create unpredictable consequences, creating a landscape of infinite potential outcomes. Navigating such a reality could be challenging. Would we become more cautious, aware that each decision carries unknowable risks? Or would we embrace the chaos, seeing this freedom as an opportunity to act without limits? Picture future recollections popping up in the here and now, like a case of déjà vu. In a universe devoid of causation, dreams might become more than just instinct, offering hints of what's to come. This has prompted some scientists to wonder if space-time has a memory system that would enable the cosmos to recall results from the past. A feedback loop in which events throughout time impact each other may be created if the universe in this model continuously refers to its past, future, and present. In a reality without causation, even our concept of free will is up for debate. Are our choices truly our own, or are they shaped by a cosmic web of interconnected events? Some philosophers argue that the breakdown of causality would challenge our perception of self-determination. We may find that our actions and thoughts are not as separate from the universe's outcomes as we assume. Rather than being detached observers, we may be part of a larger flow, with every choice linked to an intricate web across time and space. Our brains are wired to understand the world through cause and effect. But a universe without this guiding principle would force us to rethink basic cognition. Some theorists even suggest that we could evolve new senses to interpret a causality-free environment. Perhaps we would develop a quantum sense, a perception that allows us to experience events as interconnected rather than sequential, understanding time as a fluid continuum rather than a rigid line. Navigating such a reality might also require new forms of logic. The logical systems we rely on could break down without the anchor of cause and effect, and we might need to embrace a framework that accepts contradiction. This hypothetical quantum logic would accommodate ambiguity, allowing us to reconcile paradoxes as integral parts of reality rather than anomalies to be solved. Science, built on the foundation of causality, would face profound challenges if this bedrock crumbled. Our entire approach to understanding the universe relies on linking events to causes, forming predictions based on observable patterns. If causality dissolves, could this mark the end of scientific inquiry as we know it? Or would it open doors to a new era, with alternative methods that accept uncertainty and explore reality through a different lens? This new science might rely on quantum mechanics or even entirely novel frameworks that embrace ambiguity and contradiction as essential truths. This concept also raises questions about the universe's nature. Some physicists speculate that the universe may operate as a loop, where its end flows back into its beginning. If so, the breakdown of causality might be an essential part of this cycle, allowing for cosmic renewal. Perhaps the universe isn't a straightforward journey from birth to death, but a self-sustaining loop, a system where each end lays the groundwork for a fresh start. If causality collapses, consciousness itself could become central to the universe's structure. Could our minds be more than just observers, actively shaping the fabric of reality? Some theories suggest that reality emerges from consciousness and that we may influence the universe merely by thinking about it. In a causality-free universe, our awareness could play a greater role in crafting reality, suggesting that we are not just part of the cosmic drama, but co-creators in its unfolding narrative. The breakdown of cause and effect raises questions that challenge our deepest beliefs about reality, time, and human agency. This hypothetical scenario might remain purely theoretical, but it provides a glimpse into the potential mysteries at the edge of our universe's evolution. The end of causality, if it comes, would stretch our understanding of reality to its limits, forcing us to look at existence through an entirely new lens. The black hole evaporation paradox. Information lost and found. Think of a black hole as a huge area in space with such a strong gravitational attraction that not even light can escape its grasp. Hawking radiation is the source of Stephen Hawking's notion that black holes might evaporate gradually over time. The black hole is able to contract and vanish because this radiation causes energy to escape from it. However, there is a contradiction in this progressive vanishing. When a black hole disappears, what becomes of the data that was sucked into it? At its core, the black hole information paradox is this odd and seemingly elementary question. In the world of quantum mechanics, one thing that stands firmly is that information can't be destroyed. The particles that make up our universe carry information about their state, position, and properties. And even when they change form, that data isn't supposed to be lost. Theoretically, information might scatter or become unrecognizable, but it remains. Yet with black holes, this rule doesn't seem to apply. As they emit Hawking radiation and gradually lose mass, they seemingly violate the principle of information conservation, creating an apparent contradiction in the way our universe is supposed to work. This brings us to the event horizon, the boundary of a black hole, beyond which no light or information can escape. Here, the mysteries deepen. The event horizon has been considered a point of no return, but in recent years, theorists have proposed the existence of an apparent horizon, which is slightly different from the event horizon in that it may offer a way for information to escape over time, especially as the black hole nears the end of its life. According to a no-hair theorem in quantum physics, black holes are just basic particles having the three basic properties of mass, spin, and charge. This lack of hair means that black holes lack any surface features or distinguishing marks, making it impossible to identify any specific information about what has fallen into them. This again raises questions about where the specific information of any particular object entering a black hole goes. Does it just disappear? Stephen Hawking later proposed that information might actually be stored in the form of soft hair or tiny vibrations on the surface of the black hole. This concept has sparked interest, as it could hint at a way to reconcile black hole evaporation with the laws of quantum mechanics. The idea is that, rather than letting all information disappear, the black hole retains certain characteristics in its soft hair, allowing information to exist in a hidden form. But this hypothesis, while creative, still doesn't completely solve the paradox. To prevent data from falling into the black hole in its entirety, some physicists have proposed a firewall, or a physical barrier of energy at the event horizon. This idea, however, conflicts with the fundamentals of general relativity, which predicts smooth spacetime at the horizon. The firewall hypothesis implies that particles approaching a black hole would be burned up upon reaching the event horizon, ensuring no information crosses it. But this notion remains highly controversial, as it contradicts much of what we currently understand about spacetime. Black hole complementarity is another attempt at an explanation. This theory suggests that information could be both reflected at the event horizon and pass through it into the black hole's interior simultaneously, depending on the observer's perspective. In this view, information isn't destroyed or duplicated, but instead exists in a kind of dual state. Theoretical physicist Gerard 't Hooft proposed the holographic principle, which Leonard Susskind later revised, suggesting that all of a black hole's information may reside on its event horizon, a two-dimensional surface. This theory states that a black hole's 2D surface might be used to project holographic images of the 3D data contained inside. If this holds, it may suggest that the information on everything that goes into the black hole isn't completely erased, but rather preserved in a format that we aren't able to decipher just yet. Furthermore, according to the holographic principle, everything in the cosmos might be a hologram, with the three-dimensional data around us stored on a two-dimensional border. Adding to this enigma, the holographic principle also suggests that certain higher dimensional spaces, such as a black hole, could be fully described by theories in a lower dimension. This principle suggests that, theoretically, we could describe the inner workings of a black hole in terms of a two-dimensional quantum field on its surface, implying that information might actually be preserved on this boundary layer. In this case, information would be spread across the horizon as the black hole evaporates, solving the paradox by allowing information to remain encoded in this lower dimensional theory. Since a black hole should potentially continue to evaporate entirely as it loses energy via Hawking radiation, the concept of black hole evaporation has its own set of challenges. This is why physics struggles to describe what happens in the final stages of this evaporation process. At this stage, as the black hole nears total evaporation, the behavior of particles at the quantum level becomes unpredictable. The standard models break down, making it difficult to predict if information is ultimately lost or if it somehow escapes at the end of the evaporation process. A related theory, known as quantum tunneling, suggests that particles could potentially escape the black hole as it evaporates by tunneling out of it. Quantum tunneling allows particles to pass through energy barriers that would otherwise trap them, and in theory, some information could escape this way. However, the amount of information escaping would be minimal, and whether it could fully resolve the paradox remains highly uncertain. Recent scientific speculation proposes the existence of tiny particles known as black hole remnants that may persist after a black hole has dissipated. These remnants could contain all the information that fell into the black hole, preserving it at a microscopic level. While remnants offer a potential answer, there's currently no empirical evidence to support their existence, and they would require an entirely new understanding of particle physics to validate. Wormholes could theoretically connect different parts of spacetime and could potentially link two black holes, allowing information to escape from one to the other. Physicists Juan Maldacena and Leonard Susskind proposed the ER=EPR conjecture, suggesting that entangled particles, EPR pairs, could be connected by tiny wormholes or Einstein-Rosen ER bridges. This theory hints that information might be shared between two connected black holes via these entangled pairs, allowing it to remain in the universe even as black holes evaporate. The idea of black hole microstates is another theory that posits that these objects have a wealth of information about the matter and energy they contain in their many hidden variables. These microstates would each represent a unique configuration of the black hole's particles, storing information in ways we can't yet observe. Simulating black holes on quantum computers has become a recent effort to understand how information might behave in a black hole. By using simulations, physicists hope to model black hole evaporation, which could eventually reveal new insights about the information paradox. The strange behaviors we observe when contemplating black holes also bring us closer to understanding our universe's ultimate fate. Black hole evaporation and information preservation are tied to larger concepts of determinism, entropy, and even the second law of thermodynamics. If information can indeed be lost in black holes, it could mean that our universe has an inherent randomness and unpredictability, challenging the very notion of a deterministic reality where everything follows a strict cause and effect. Time's reversal, the universe in rewind. Time shapes our reality, an unbroken flow from past to future. But what if, at the universe's end, this steady march of time fragmented, with the direction of time itself splintering? Instead of a linear progression, imagine a cosmos where time flows unpredictably, reversing and twisting in unexpected ways. This altered flow could upend everything we know, changing the very forces that govern our existence. A universe with reversed time would mean that past and future influence each other, creating a complex web of interactions. Instead of a simple rewind, such a scenario would see moments branching in unpredictable directions. Events, once separated by time, could intertwine, reshaping the chronological order and defying our standard understanding of causality. Would such a reversal affect the fundamental forces that shape our universe? Gravity, for example, could shift from an attractive force to a repulsive one, tearing galaxies apart and disrupting the balance that holds planets in orbit. Stars could explode outward, and the intricate gravitational web holding cosmic structures together would unravel. Electromagnetism might also invert, causing particles with like charges to attract instead of repel, altering the behavior of matter at a basic level. Familiar interactions in chemistry, electricity, and magnetism could take on strange new forms, potentially rendering technology unrecognizable. The nuclear forces that bind atomic nuclei might weaken, leading to the breakdown of matter itself. If time's flow truly reversed, could the expansion of the universe, which currently pushes galaxies apart, slow down or even reverse? Cosmologists suggest that a big crunch might occur, where galaxies rush back toward each other, reversing the universe's expansion. Everything would contract, potentially collapsing into a dense singularity, mirroring the Big Bang in reverse, a cosmic rebirth from singularity back to singularity. Entropy measures disorder, and in our familiar universe, it only increases. In a time-reversed scenario, however, entropy could decrease, challenging our understanding of the second law of thermodynamics. Imagine a reality where broken items reassemble, and chaos gives way to order. If time reverses, systems could spontaneously self-organize, as if rewinding from complexity to simplicity. In this reversed reality, black holes could behave differently. Currently, they act as points where time seems to freeze and matter is compressed to extremes. But if time flowed backward, black holes might expel matter instead of absorbing it. This could open a doorway to the past, allowing us to observe the universe rewinding from its final stages back to its origin. We might witness galaxies forming, stars condensing, and the Big Bang as an active event rather than a historical one. Quantum mechanics, particularly the phenomenon of entanglement, could provide clues to this strange world. Entangled particles influence each other regardless of distance, And this connection might even allow effects to precede causes, a concept known as retrocausality. Could particles communicate across time, creating a feedback loop where future events impact the past? This raises questions about free will. In such a universe, are our actions predetermined by future events beyond our control? The CPT theorem in physics suggests a symmetry between charge, parity, and time. If time reverses, charge and parity could also invert, creating a universe of antimatter and mirror-like structures. This mirror universe would look familiar, yet reversed, challenging our understanding of fundamental symmetries and revealing alternative versions of reality. Some researchers speculate that the universe might possess a memory encoded within spacetime, potentially storing information from both the past and future. In a time-reversed universe, we might gain access to these cosmic memories, witnessing events from the future as though they were past occurrences. Such a reality would let us glimpse the entire timeline of the universe, from the Big Bang to its end, as if it were all happening simultaneously. We could even use insights from the universe's own future to shape its course, guiding its evolution in ways we cannot currently imagine. Could consciousness, in a universe with reversed time, transcend our linear perception of past, present, and future? Some theorists suggest that if time's direction is fluid, we might experience memories of events yet to come, effectively communicating with our past selves. This ability to perceive the future as a memory could allow humans to make choices informed by what's ahead rather than what's behind. Our brains are hardwired to experience time as a one-way street. Would a time-reversed existence cause cognitive dissonance or a breakdown in our perception? Could we adapt to this inverted reality, developing new ways to comprehend events without the anchor of linear time? Some suggest that we might evolve quantum senses to interpret a causality-free universe, where time is not a strict line, but a complex, interconnected mesh. Science relies on causality, the idea that we can study events by linking causes to effects. In a time-reversed universe, causality would lose its meaning, fundamentally challenging scientific methodology. Would this signal the end of scientific inquiry? Or could it lead to a new scientific paradigm, one that embraces uncertainty and explores a universe without predictable outcomes? Perhaps we'd find methods that combine quantum mechanics with new frameworks, adapting to study a world where time's arrow is no longer fixed. Could time reversal serve as a cosmic reset, a way for the universe to renew itself? Some scientists propose that the universe may exist on a cyclical timeline, expanding and contracting in an endless loop. In this view, a reversal of time would allow the universe to contract, condensing into a big crunch that sparks a new Big Bang, a self-perpetuating cycle of birth, expansion, and collapse. Consciousness could play a central role, not just in observing reality, but in actively shaping it. If reality is not a fixed narrative, but a fluid, interconnected tapestry, then our awareness might influence the universe at a fundamental level. This idea suggests that we are not merely passive witnesses to a predetermined cosmos. Rather, we may be co-creators, with our thoughts and actions directly impacting the structure of reality. The reversal of time challenges the core of our understanding of the universe and our place within it. Is time an illusion created by our consciousness? Could a time-reversed universe reveal a more complex reality, where time flows in many directions, not just forward? Perhaps time, like a river, contains hidden currents and eddies, its true nature beyond our everyday experience. In a universe where time's arrow can reverse, the very notion of existence becomes flexible, open to possibilities beyond our conventional understanding. The concept of time reversal invites us to rethink our assumptions about reality, causality, and consciousness. It suggests that the universe may be more than a simple progression from beginning to end. It might be a multidimensional experience where past and future merge, and reality reshapes itself in ways that defy our current logic. Vacuum decay, the cosmic reset. The universe appears stable and unchanging, but beneath this facade lies the possibility of a catastrophic event known as vacuum decay. This concept arises from theoretical physics, suggesting that our universe might exist in a false vacuum, a metastable state that appears stable but could transition to a more stable state with lower energy. Visualizing the universe as an energy landscape helps illustrate this idea. Imagine a terrain of hills and valleys representing different energy states. Our universe currently resides in a shallow valley, the false vacuum, which seems secure but is susceptible to a sudden shift. A quantum fluctuation, a random change at the smallest scales, could trigger the transition to the true vacuum, sending the universe into a deeper valley and initiating a profound transformation. This transition would not be gradual. It would unleash a bubble of true vacuum that expands at the speed of light, consuming everything in its path. As it spreads, it would alter the fundamental forces and particles that constitute reality. Stars would extinguish, planets would disintegrate, and galaxies would be obliterated. The laws of physics as we know them would change, potentially rendering the universe uninhabitable. Exploring this scenario raises critical questions about the potential impact on the cosmos. The expansion of the true vacuum bubble would be unstoppable and undetectable until it arrives, giving no warning or opportunity for escape. Civilizations across the universe would be unaware of the impending transformation, which would occur instantaneously on a cosmic timescale. Despite its destructive nature, some theories suggest that vacuum decay might not signify the absolute end of existence. Within the bubble of true vacuum, new physical laws and constants could emerge, potentially giving rise to a different universe. This new reality might allow for the formation of new structures, possibly even life, albeit in forms beyond our current understanding. Examining the stability of our universe, scientists have studied fundamental particles like the Higgs boson, discovered in 2012 at the Large Hadron Collider, LHC. The Higgs boson plays a crucial role in particle physics. Calculations based on the Higgs field and particle interactions suggest that our universe is in a metastable state. This means that while it appears stable, there is a possibility, albeit extremely remote, that it could transition to a true vacuum. Delving into quantum mechanics reveals the inherent unpredictability of the quantum realm. Vacuum decay highlights how quantum fluctuations can have monumental consequences. Even the seemingly empty space between particles holds the potential for significant changes that could reshape the cosmos. The prospect of vacuum decay introduces profound philosophical considerations about the nature of existence and the fragility of reality. It confronts us with the idea that the fundamental laws governing our universe could be subject to sudden change, driven by processes beyond our control or detection. Scientists continue to explore this concept to understand the universe's stability better. High-energy particle collisions in accelerators like the LHC allow researchers to probe conditions similar to those just after the Big Bang. These experiments help refine models predicting the likelihood of vacuum decay, contributing to our comprehension of fundamental physics. Some theoretical frameworks, such as the multiverse theory, propose that our universe is just one of many, each with its own vacuum state and physical laws. In this context, vacuum decay in one universe might lead to the birth of another, suggesting a cosmic cycle of creation and transformation. This perspective offers a broader view of existence, where the end of one universe becomes the beginning of another. Understanding vacuum decay also has implications for cosmology and particle physics. It challenges scientists to reconcile quantum mechanics with general relativity, aiming for a unified theory that can describe such extreme events accurately. Advances in theoretical physics could shed light on the mechanisms behind vacuum decay and the true nature of the vacuum state. In practical terms, the probability of vacuum decay occurring in the foreseeable future is exceedingly low. Estimates suggest that the timescale for such an event is many orders of magnitude longer than the current age of the universe. Therefore, while scientifically intriguing, vacuum decay does not present an immediate existential threat. Considering vacuum decay encourages appreciation for the delicate balance of forces that allow the universe to exist in its current form. It highlights the significance of fundamental physical constants and how slight variations could lead to vastly different realities. For instance, minor changes in the strength of the electromagnetic force or gravity could prevent stars and galaxies from forming. Advancements in observational astronomy and particle physics may one day provide more definitive answers about the universe's stability. Precision measurements of cosmic microwave background radiation, the afterglow of the Big Bang, could reveal subtle clues about the universe's fundamental properties. Additionally, further discoveries related to dark energy and dark matter might offer insights into the forces influencing cosmic evolution. The exploration of vacuum decay exemplifies humanity's quest to understand the deepest aspects of reality. It pushes the boundaries of science and philosophy, inviting contemplation of our place in a universe that is both immense and intricate. While the concept is daunting, it also inspires awe at the profound interconnectedness of cosmic phenomena. Researchers are also investigating the role of cosmic inflation, a rapid expansion of the universe that occurred fractions of a second after the Big Bang, in relation to vacuum stability. Understanding this relationship could provide insights into why the universe settled into its current state and how it might evolve in the distant future. Another area of interest is the study of cosmic phase transitions. Just as water can exist in different phases, ice, liquid, vapor, the universe's fields can undergo phase changes. These transitions can have significant implications for particle masses and force strengths. By studying these processes, scientists aim to understand whether such transitions could trigger vacuum decay. The potential implications extend to the field of astrophysics as well. For example, extreme environments like neutron stars or black holes might offer conditions where vacuum decay could be more likely, albeit still highly improbable. Observations of these objects could provide indirect evidence supporting or refuting aspects of vacuum decay theories. Furthermore, the concept encourages interdisciplinary collaboration. Physicists, cosmologists, and philosophers work together to explore the ramifications of vacuum decay, each bringing unique perspectives. This collaborative effort enriches the dialogue surrounding fundamental questions about existence and the universe's ultimate fate. While the idea of a sudden catastrophic transformation is unsettling, it underscores the importance of continued research and exploration. Humanity's drive to understand the universe has led to remarkable discoveries, from the smallest subatomic particles to the largest cosmic structures. Each advancement brings us closer to answering profound questions about reality. Negative gravity, the repulsive force. The idea of negative gravity is foreign to the accepted laws of nature that govern our everyday lives. Unlike conventional gravity, which attracts objects toward one another, negative gravity proposes a repulsive force that pushes objects apart. While this idea is speculative, it intersects with areas of cosmology that study dark energy and the accelerating expansion of the universe. Understanding how such a force could operate involves exploring concepts like negative pressure, vacuum energy, and the behavior of exotic matter. Observations in the late 1990s revealed that the universe is not just expanding, but doing so at an accelerating rate. This acceleration suggests the presence of a force strong enough to counteract the gravitational attraction between galaxies. Dark energy, which is estimated to make up about 68% of the universe's total energy content, is theorized to drive this acceleration. Some scientists hypothesize that this dark energy could be associated with a form of negative gravity, a repulsive force that opposes the pull of normal gravity. Delving into the nature of dark energy, one hypothesis involves vacuum energy, the energy present in empty space. Quantum field theory suggests that even a perfect vacuum is not truly empty, but filled with temporary fluctuations of energy. These fluctuations might contribute to a form of negative pressure, effectively acting as a repulsive gravitational force on cosmic scales. This negative pressure could cause the expansion of the universe to accelerate, pushing galaxies apart more rapidly over time. Einstein's general theory of relativity traditionally describes gravity as an attractive force resulting from the curvature of spacetime caused by mass and energy. However, Einstein himself introduced the cosmological constant as a term in his equations to allow for a static universe, which was the prevailing belief at the time. After the discovery of the universe's expansion, the cosmological constant was reinterpreted to account for the accelerating expansion observed. It now serves as a mathematical representation of dark energy in Einstein's equations, accommodating the repulsive effect needed to explain current cosmological observations. Exploring the concept further, the idea of exotic matter introduces the possibility of negative mass. Negative mass is a hypothetical concept in physics where mass would respond to forces in opposite ways compared to normal mass. If negative mass existed, it would accelerate in the opposite direction of an applied force. In terms of gravity, negative mass would repel positive mass, potentially creating regions of space where gravitational effects are reversed. While no experimental evidence for negative mass exists, theoretical models sometimes incorporate it to explore phenomena like cosmic inflation and the stabilization of wormholes. The early universe underwent a period of rapid expansion known as cosmic inflation. This expansion can be modeled by a high-energy field with properties similar to those of a substance with negative pressure. The inflationary epoch stretched spacetime so rapidly that regions which were once close became causally disconnected. The mechanism behind this expansion is still not fully understood, but it is often associated with a scalar field called the inflaton, which drives the exponential growth of the universe. This process resembles the effects that negative gravity would have on spacetime. Examining the laws of physics, Newton's third law states that for every action, there is an equal and opposite reaction. In the context of negative gravity, this principle raises questions because a repulsive gravitational force doesn't fit neatly into this framework. However, general relativity supersedes Newtonian physics on cosmic scales, and the equations of general relativity can accommodate repulsive effects through the cosmological constant or other forms of energy momentum that lead to spacetime expansion. Gravitational waves, ripples in the fabric of spacetime caused by accelerating masses, have provided new insights into gravity. Detected first in 2015 by the LIGO collaboration, these waves confirm predictions of general relativity. While gravitational waves themselves don't imply negative gravity, studying them enhances our understanding of gravitational phenomena under extreme conditions. They offer a window into events like black hole mergers, where gravity behaves in ways that are not fully understood, potentially opening avenues to explore modified theories of gravity. Quantum fluctuations in the early universe could also play a role in explaining dark energy and the observed acceleration of cosmic expansion. The energy associated with these fluctuations might contribute to the vacuum energy density, affecting the dynamics of the universe on large scales. Some mathematical models, such as those involving anti-de Sitter space, explore spacetimes with constant negative curvature, while our universe is observed to have a nearly flat or slightly positive curvature, de Sitter space. Studying these models helps physicists understand how different geometries impact gravitational behavior. In theoretical physics, concepts from string theory and quantum mechanics sometimes predict phenomena that challenge classical intuitions. While standard models do not predict particles with negative mass, certain speculative theories allow for solutions where exotic properties emerge under extreme conditions. These ideas are highly theoretical and lack experimental verification, but contribute to the broader exploration of how gravity might behave differently in various contexts. Black holes and wormholes are areas where gravity reaches its most intense manifestations. In black hole thermodynamics, Hawking radiation describes how black holes can emit particles due to quantum effects near the event horizon, potentially leading them to lose mass over time. While negative gravity isn't directly invoked in this process, the interplay between quantum mechanics and gravity in such extreme environments continues to challenge our understanding and could reveal new physics. Wormholes, hypothetical tunnels connecting distant points in space-time, require exotic matter with negative energy density to remain stable, according to general relativity. This negative energy would counteract the gravitational pull that would otherwise cause the wormhole to collapse. Though purely theoretical at this point, the concept of negative energy density is essential in the equations that describe traversable wormholes, highlighting the role of unconventional gravitational effects in advanced theoretical models. Cosmologists have proposed scenarios like the Big Rip, where the acceleration of the universe's expansion becomes infinite in a finite time, due to a form of dark energy with an equation of state even more extreme than a cosmological constant. In this hypothetical situation, the repulsive effect becomes so strong that it overcomes all other forces, tearing apart galaxies, stars, planets, and eventually atoms themselves. This concept illustrates the potential dramatic consequences of continued acceleration, but remains speculative and depends on specific properties of dark energy that are not confirmed by observations. The study of cosmic strings, hypothetical one-dimensional topological defects in spacetime, also intersects with discussions about gravity. While cosmic strings are predicted to have enormous mass and thus gravitational effects, they do not inherently involve negative gravity. However, their influence on spacetime could produce gravitational lensing effects or contribute to the overall dynamics of the universe's expansion, providing another avenue to explore gravitational phenomena. Einstein's equivalence principle, a cornerstone of general relativity, states that gravitational mass and inertial mass are equivalent. Introducing negative mass or negative gravity into physical theories challenges this principle. If negative mass existed, it would imply that gravitational and inertial masses could differ in sign, leading to behaviors that contradict well-established physical laws. Such considerations drive physicists to carefully examine the consistency of theoretical models that include negative gravity. In certain speculative models, negative gravitational effects might prevent the formation of black holes by counteracting the gravitational collapse of massive stars, while current understanding supports that black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. Introducing a repulsive force could alter this outcome. These ideas remain theoretical and are not supported by observational evidence, but contribute to ongoing discussions about gravity under extreme conditions. The concept of a multiverse, where multiple universes with different physical laws might exist, allows for the possibility that some universes could have repulsive gravity as a fundamental force. While this idea is beyond current empirical science, it provides a framework for considering how different gravitational behaviors could arise in different contexts, expanding our perspective on what is possible within the realm of physics. Speculating on the technological implications, if negative gravitational effects could be harnessed, they might enable advanced propulsion methods or space travel concepts like warp drives. These ideas often appear in science fiction and involve bending or manipulating spacetime to achieve faster-than-light travel. While intriguing, they remain purely speculative and face significant scientific and engineering challenges. Ringularity, the singular circle. A ringularity is a form of singularity unlike any traditional point singularity found in standard black holes. In astrophysics, singularities represent regions of space where gravity compresses matter to an infinite density. But in rotating black holes, known as Kerr black holes, the singularity is not a point, but rather a loop, a one-dimensional ring. This shift from a point to a ring has huge implications for our understanding of gravity, space-time, and even the fabric of the universe. In a traditional black hole, everything collapses toward a single point in the center. But in a Kerr black hole, extreme spinning stretches this point into a ring. This ringularity opens up an entirely new dimension to consider. The centrifugal force from the rapid rotation counteracts the gravitational pull, creating a region in the middle of the ring where gravity might theoretically be weak enough to allow matter or even light to pass through. It's a wild concept, one that suggests these ring-shaped singularities could act like portals or gateways to other parts of the universe, or even other universes entirely. In fact, ringularities have the potential to generate temporal loops, according to certain theories. Close proximity to the ring may cause an item to undergo what physicists refer to as closed time-like curves, CTCs. Put simply, CTCs are space-time pathways that encircle one another, potentially enabling a particle to traverse time and ultimately return to its initial location. This concept of time loops presents profound implications for causality and the very nature of time. If ringularities allow these time loops, then particles, or theoretically even spaceships, could travel through time in ways that defy our current understanding. The event horizons are another distinctive feature of a ringularity. In standard black holes, there's a single event horizon, a boundary where gravity becomes so intense that not even light can escape. However, ringularities are theorized to have multiple event horizons. These could form complex boundary layers within the black hole, marking zones of varying gravitational intensity. Some models even suggest there could be safe areas within these boundaries, where the gravitational forces aren't quite as deadly as they are near a traditional singularity. This layering challenges the classic point of no return view of black holes, and raises the possibility that different regions inside a black hole could have drastically different physical properties. The shape of the event horizon itself could change, influenced by the spinning ringularity. Whereas the event horizon of a traditional black hole is a perfect sphere, the horizon surrounding a ringularity could be stretched into an elliptical or even toroidal, donut-like shape. This would mean that the shadow cast by a black hole with a ringularity, when observed from afar, wouldn't resemble the uniform circular shape that's often expected. Instead, its silhouette could appear warped, elongated, or even have a gap in the middle, depending on the angle of observation and the speed of rotation. The impact of frame dragging is another intriguing feature of ringularities. This happens when spacetime is dragged along by a huge revolving object, such as a Kerr black hole. When things are close to a ringularity, they are dragged in a complicated manner as they spiral around the singularity. Interactions with this distorted spacetime may cause light and other particles to take circuitous rather than straight routes. Instead of plunging straight into the singularity, particles seem to dance inwards thanks to these frame-dragging effects. This is another example of how ringularities may cause gravitational phenomena that are completely new to us when they spin extremely fast. For those who speculate about the ultimate fate of information in black holes, ringularities open up even more complex questions. In physics, the information paradox describes a puzzling situation where information about matter that falls into a black hole seems to be lost forever. This conflicts with the laws of quantum mechanics, which state that information can never be truly destroyed. Ringularities could add another layer to this paradox by creating unique zones within the black hole, where information behaves differently from the way it does around a standard point singularity. The presence of a one-dimensional ring, rather than a zero-dimensional point, might allow for new possibilities in the way information is stored or transferred in extreme gravitational conditions. Hawking radiation, the process through which black holes gradually lose mass and evaporate, might also behave differently in the presence of a ringularity. Since Hawking radiation depends on the geometry of the black hole, a ringularity's structure could alter the amount and nature of radiation emitted. This could mean that black holes with ringularities dissipate energy at a different rate or even in distinct patterns, potentially offering a new way to distinguish between types of black holes based on their radiation signatures. The existence of negative energy near a ringularity adds another layer of complexity. Theoretical models suggest that the extreme spinning could generate regions of negative energy density around the ring. This negative energy is essential for theoretical constructs like stable wormholes, as it could counteract the crushing forces of gravity and keep the throat of a wormhole open. If negative energy does exist near a ringularity, it could pave the way for the formation of stable paths through spacetime, paths that don't collapse under the weight of their own gravitational pull. Furthermore, dark matter may have a special function in the vicinity of ringularities. Since we still don't fully understand how dark matter interacts with gravity in extreme environments, the gravitational influence of a ringularity might affect dark matter differently than a standard black hole. The interaction could lead to unusual behaviors, potentially causing dark matter to clump or disperse in new ways near the ring. Studying these interactions could offer new clues into the nature of dark matter and how it behaves under extreme gravitational forces. The possibility of stable orbits is another one of the most mysterious features of ringularities. In a standard black hole, no stable orbits can exist within the event horizon. However, some models propose that near a ringularity, there could be regions where objects or even light could orbit stably for extended periods of time. These stable orbits would create a gravitational setup that's drastically different from anything we see in more familiar astronomical settings. Imagine a particle caught in a gravitational tug-of-war, circling the ringularity indefinitely rather than being pulled inward or pushed outward. Gravitational waves, which are spacetime ripples caused by the collision of large objects, may potentially provide information on ringularities. When black holes with ringularities collide, the gravitational waves they produce could carry unique signatures, distinguishable from waves generated by collisions involving traditional point singularities. Detecting these unique gravitational wave patterns would allow us to identify ringularities indirectly and study their properties without ever seeing them directly. Ringularities may also provide insights into the cosmic censorship hypothesis. This hypothesis suggests that singularities are always hidden behind event horizons, making them impossible to observe directly. However, if ringularities differ significantly from point singularities, they might challenge this rule. The specific geometry and rotation of a ringularity could theoretically expose parts of the singularity in a way that's observable from outside the event horizon, allowing us to catch a glimpse of these mysterious objects and test the boundaries of this hypothesis. The unusual structure of ringularities might even influence gamma-ray bursts, brief, intense emissions of energy thought to be associated with massive explosions. If matter interacts with a ringularity violently, it could produce bursts of energy that differ from typical gamma-ray bursts, both in intensity and duration. Observing these variations could provide a window into the behavior of matter under the most extreme conditions imaginable. If these ring-shaped singularities exist, they could occupy the centers of certain galaxies, particularly those with highly energetic cores. The gravitational influence of a ringularity at a galactic center could affect how stars and other objects move, influencing the formation and dynamics of entire galaxies in ways we've yet to fully understand. If these cosmic giants truly exist at galactic cores, they could help explain the highly energetic phenomena observed in some galactic centers. The very nature of ringularities forces us to reevaluate our long-held assumptions about space, singularities, and gravity. The notion of a ringularity unites the known with the speculative, offering a glimpse of how physics may unfold at the universe's periphery, in a field of physics where theory frequently supersedes experimental proof. Investigating the characteristics of these hypothetical objects allows us to reevaluate the nature of space, time, and gravity, regardless of their actual existence. The holographic universe. Unraveling, reality's illusion shattered. As a theory that challenges our current conception of reality, the idea of a holographic cosmos is among the most bizarre and fascinating in contemporary physics. This idea, which originated from research on black holes, suggests that all of our familiar three-dimensional reality could essentially be a projection from a lower dimensional boundary, as if the universe were a cosmic hologram. Rooted in the study of string theory, quantum mechanics, and cosmology, this theory provides potential answers to some of the most profound questions in physics, and raises further mysteries about the nature of space, time, and reality itself. The holographic principle began as a solution to a problem with black holes. Physicists noticed that when an object falls into a black hole, its information seems to vanish, contradicting the rules of quantum mechanics, which state that information must be preserved. To address this, researchers proposed that all of the information inside a black hole could be encoded on its two-dimensional surface, the event horizon, rather than within its three-dimensional volume. This led to a much broader speculation. If information could be stored on the surface of a black hole, could the entire universe work this way? Could all of our three-dimensional world actually be encoded on a distant two-dimensional boundary? One formulation of this concept is the anti-de Sitter conformal field theory, ADS-CFT correspondence. It's a theoretical framework that describes how a three-dimensional world with gravity can be mathematically equivalent to a two-dimensional world without gravity on its boundary. Although our universe doesn't match the specific structure required by ADS-CFT, it provides a potential model for how a holographic universe might work. In this model, space itself could emerge from the interplay of forces on a distant two-dimensional boundary, and gravity, as we experience it, might simply be a mirage resulting from these processes. Among the most intriguing consequences of this theory is the possibility that dimensions are not what they appear. In the holographic universe, depth and volume could be illusions, just as a flat hologram can give the impression of depth without actually having any. This leads to the mind-bending idea that our sense of three-dimensional space might be a kind of projection, emerging from simpler data encoded on the boundary of the universe. Quantum entanglement, a strange phenomenon where particles remain connected regardless of distance, might be essential for understanding how a holographic universe could project depth. Some scientists suggest that the structure of spacetime is actually woven together by entangled particles on this boundary. In other words, the very fabric of our reality might be nothing more than a complex web of relationships between particles, linked in ways that defy distance as we typically understand it. The holographic principle also implies limits on information density, known as entropy bounds. Just as the information on a hologram is limited by the surface area, the amount of information that can exist in a given region of space is limited by the surface area of its boundary. This has profound implications for physics and thermodynamics. In a holographic model, increasing entropy doesn't expand volume, but adds more surface area of encoded information. A fascinating observation is that, according to the holographic principle, the edge of the universe could potentially hold all the information that identifies our world and ourselves, including planets, humans, and even individual particles. This edge would be an incredibly distant two-dimensional surface that somehow gives rise to all of the complexity we see in the three-dimensional world. Cosmology is another fascinating area where the holographic principle has found use. The early universe's rapid expansion, known as cosmic inflation, could be modeled as a projection from an inflationary surface. This means that our observable universe might be a kind of bubble, formed from processes on a distant, invisible boundary. Some scientists are now examining the cosmic microwave background, the faint afterglow of the Big Bang, for clues that might support this holographic structure. If this afterglow contains certain kinds of patterns, it could provide evidence that the universe is indeed holographic. This model also raises interesting questions about the fundamental nature of particles and fields. In a holographic view, particles might not be tiny points, but rather emergent properties resulting from interactions on the universe's edge. Quantum field theory, which describes particles as excitations in fields, could thus be reinterpreted as describing patterns on this two-dimensional boundary. Holography also has the potential to radically alter our view of quantum gravity, the long-sought theory that would finally bring all the basic forces into harmony. In traditional models, gravity is challenging to describe at quantum scales. But in a holographic model, gravity in a higher dimensional space, our three-dimensional world, could be seen as an effect of fields in a lower dimensional boundary. This might offer a more straightforward way to calculate gravitational interactions and provide a path toward a complete theory of quantum gravity. There may also be links between dark energy and dark matter in the holographic cosmos. These mysterious components make up most of the universe's mass energy but don't interact with light or ordinary matter in a way that we can detect directly. Some theories suggest that dark energy and dark matter could be understood as effects emerging from the interactions on the universe's boundary, rather than entities within our three-dimensional space. If this were true, it could help explain why these forces seem so pervasive and powerful, yet remain so elusive. Common ideas like volume, location, and distance take on new meaning in the context of a holographic cosmos. In a universe where space is projected from a distant surface, these concepts might not have the intrinsic meaning we assign to them. Instead, they might be emergent, arising from relationships encoded on the boundary. This might also help explain quantum indeterminacy, where particles don't seem to have definite positions or velocities until measured. In a holographic view, these uncertainties could be the result of our limited perspective on a projection, rather than a fundamental property of particles. There are those in the scientific community who see the holographic principle as evidence of a digital world in which all information exists in limited bits. If the universe is fundamentally digital, then what we experience as continuous fields and flows might actually be granular on a small enough scale, much like how a digital image is composed of individual pixels. This idea aligns with information theory, which studies how data is stored and processed and could play an essential role in understanding physics in a holographic universe. A powerful analogy for the holographic universe is virtual reality. In a VR environment, a user experiences depth and space, but these are only illusions created by the software. The computer simulates a 3D world using 2D screens, and our brain interprets it as depth. In a holographic universe, our senses and perceptions might be tuned to interpret holographic information as a three-dimensional world, tricking us into seeing depth where there is only surface. For skeptics, the holographic principle's speculative nature and lack of direct evidence pose significant hurdles. Testing such a theory is challenging, as it requires experimental methods beyond our current technological reach. However, scientists are exploring indirect evidence, like entropy bounds and patterns in cosmic background radiation, that might offer hints of a holographic universe. According to the holographic principle, a system's surface area, not its volume, grows as its entropy increases. This would mean that as the universe expands, what's actually increasing might be the amount of information stored on its boundary rather than the physical space within it. This suggests that our observable universe, filled with stars, galaxies, and planets, could be a vast entropic hologram, expanding in information rather than physical volume. The relationship between black holes and holography is particularly significant. Black holes are areas of intense gravitational pull, where nothing, not even light, can escape once it crosses the event horizon. According to the holographic principle, all the information about objects falling into a black hole is encoded on the event horizon, which behaves like a holographic boundary. This concept has led scientists to view black holes as unique testing grounds for understanding how space, information, and even time interact. In classical physics, causes precede effects in a predictable manner, but in a holographic universe, these relationships might not be so straightforward. This could mean that causality, like distance, is an emergent property rather than a fundamental feature of reality. The interconnectedness of entangled particles across vast distances suggests that in a holographic model, events might be bound by information patterns on the boundary rather than conventional cause and effect relationships. The holographic principle, if true, would mean that all the mysteries of the cosmos, from the nature of dark matter to the reason behind quantum uncertainty, might ultimately be understood as features of an encoded boundary. The idea that reality itself could be a kind of grand cosmic hologram is a profound shift in how we see the universe. In exploring the holographic universe, we confront the possibility that what we know as reality is only a shadow, a projection from a much stranger, deeper structure that challenges the very foundations of physics. Quantum foam, spacetime's chaotic sea. Quantum foam might seem like a distant concept, yet it's thought to be a fundamental part of our universe's structure. At scales smaller than atoms, spacetime isn't smooth or flat, but turbulent, like a constantly churning ocean. Just as waves and bubbles form and burst on the ocean's surface, quantum foam depicts spacetime filled with tiny bubbles, or regions of fluctuating energy. These bubbles form and disappear within fractions of a second, driven by the high energies and tiny distances at the Planck scale, around 10 to the power of -35 meters. To visualize this is nearly impossible, but physicists believe that this dynamic, fluctuating spacetime represents the true foundational fabric on which the universe operates. What gives rise to this bubbling quantum foam? At the heart of it lies Heisenberg's uncertainty principle, a cornerstone of quantum mechanics. This principle tells us it's impossible to know certain pairs of properties like position and momentum with absolute precision. The more precisely one is known, the less precisely the other can be known. In the chaos of quantum foam, this uncertainty manifests as constant fluctuations in energy and position. Virtual particles pop into existence and vanish within incredibly short spans of time. These particles don't last long enough to be observed directly, but they create a sea of energy, a constant churn beneath the surface of reality. Some theoretical physicists wonder if the tiny bubbles of quantum foam could contain microscopic wormholes. These wormholes would act as tunnels through space-time, theoretically allowing particles to jump across tiny distances. However, these wormholes, if they exist, would be far too small and short-lived to allow any practical passage. They'd be more like brief flickers, vanishing before any information could travel through them. Still, their existence could imply a wild possibility, that even the smallest distances in space have strange shortcuts woven into them, even if they're on scales far too tiny to observe. On larger scales, space-time seems smooth, but at the level of quantum foam, geometry breaks down. Classical geometry, with its fixed points, lines, and distances, fails to describe what's happening. In this chaotic space, there's no reliable way to measure exact positions. The distances themselves seem to shift, twist, and distort. This chaotic geometry is often described as non-Euclidean, meaning it doesn't follow the simple rules we're used to in everyday shapes and lines. At the Planck scale, we're in a world where measurements become a guessing game, as space itself twists and vibrates in unpredictable ways. This leads us into the fascinating world of quantum gravity, which is now under intense investigation by scientists, and the intriguing possibility that quantum foam might have an effect on gravity at extremely microscopic sizes. Quantum gravity is an attempt to understand gravity, which usually acts smoothly on large objects, within the chaotic environment of quantum mechanics. Because quantum foam distorts space-time, it might affect how gravity behaves. This also ties into the search for a theory that unites quantum mechanics and general relativity, which describes gravity on larger scales. Quantum foam could be the missing link that helps bridge these two areas of physics. These quantum fluctuations are incredibly short-lived. The particles in quantum foam exist for only the briefest possible moments, about 10 to the power of -43 seconds, known as Planck time. During this span, the particles appear and vanish in a flash. This rapid turnover of energy creates a turbulent sea at the smallest scales. The bubbles in this foam don't last long enough to stabilize or form recognizable shapes. They're constantly replaced by new fluctuations, keeping space-time in a perpetual state of unrest. What's fascinating is that the cosmological constant, which drives the accelerated expansion of the universe, might be influenced by quantum foam. In cosmology, the cosmological constant refers to the slight, steady expansion of the universe, even when no traditional energy is applied. If quantum foam adds small, unpredictable amounts of energy into spacetime, it might explain why the universe is expanding slightly faster than expected. This raises the idea that spacetime's chaotic foundation isn't just a localized phenomenon. It could be influencing the very fabric of the cosmos on a grand scale. This also suggests that spacetime isn't a smooth container for matter and energy, but instead an emergent phenomenon arising from quantum foam's chaotic interactions. In some theories, spacetime could be an effect rather than a fundamental component. In other words, what we think of as space and time might be born out of the interactions in quantum foam, much like water forms from individual hydrogen and oxygen atoms. This challenges our intuition about reality, suggesting that spacetime might be more like an illusion arising from deeper, more chaotic forces. Quantum foam also implies that spacetime has a granular or pixelated structure, countering the idea of it being a smooth continuum. Just as a photograph looks continuous until you zoom in close enough to see the individual pixels, spacetime may seem continuous until you observe it at scales where quantum foam dominates. This granularity could mean that spacetime has a finite structure and is chunky at its core. If true, this would mean spacetime isn't infinitely divisible, a concept that shakes up classical physics, which assumes space can be split infinitely without losing structure. The energy within quantum foam is also thought to create what's known as vacuum energy. Even in the emptiest regions of space, vacuum energy ensures that there's a background hum of activity. This residual energy might contribute to the universe's expansion, meaning that empty space isn't truly empty. Instead, it's full of constantly shifting particles and energy. Vacuum energy isn't directly observable, but its effects are, as it appears to act as a form of anti-gravity in the fabric of space. Also, according to quantum foam, Space-time can't be perfectly measured or pinned down. In classical physics, measurements are straightforward, but in quantum foam, uncertainty rules. This chaotic backdrop means that each attempt to measure it produces different results. Space-time becomes less of a rigid framework and more of a fluctuating environment, where any exact measurement is, at best, temporary. This lack of stability contrasts with the predictable measurements we experience on human scales. In addition to quantum foam, one of the most mind-bending ideas is the holographic principle. This theory proposes that our cosmos may really be a flat 2D surface, superimposed with a 3D representation of certain information. Quantum foam may be the basis for this vision, according to some physicists. Space-time may be an illusion generated by interactions on a distant surface if quantum foam is analogous to pixels on a screen. This suggests that our perception of reality may be more akin to a hologram than a physical, three-dimensional building. In the realm of quantum foam, particles are also thought to become entangled across space-time. Entanglement is a phenomenon where particles share information instantly, regardless of the distance between them. In quantum foam, particles might become entangled due to their close proximity, meaning that changes in one affect another, no matter how far they are in conventional space-time. This interconnectedness could mean that quantum foam acts like a web, where each point affects the others in unpredictable ways. There's also speculation that dark energy, the mysterious force causing the universe to expand at an accelerating rate, could be tied to quantum foam. If quantum foam fills every corner of space-time, its fluctuations might generate enough residual energy to influence cosmic expansion. This connection could provide insights into why dark energy exists and why it's so difficult to detect directly. Quantum foam is central to quantum field theory, where fields are not calm or flat, but filled with constant particle creation and annihilation. Particles in these fields don't stay fixed. They're always shifting, forming, and disappearing. This continual activity adds to the picture of a chaotic, restless space-time. This idea that quantum foam underlies even the empty space challenges our classical view of nothingness. True emptiness seems impossible when space-time itself is a constant swirl of energy and particles. At the Planck scale, emptiness vanishes, replaced by a frenetic sea of energy. This has vast implications, as it means that even a total vacuum is filled with quantum activity. Some experiments aim to find indirect evidence of quantum foam, though detecting it directly is beyond current technology. Ideas include examining cosmic rays, which travel vast distances through space, to see if they've been subtly altered by quantum foam. Another approach involves studying light from distant stars to detect any scattering effects that quantum foam might cause. These experiments are in their early stages, but could one day offer a glimpse into the chaotic microstructure of space-time. Quantum foam may also have an impact on particle physics. Space-time fluctuations may alter the basic principles controlling particles and their interactions. Depending on the nature of the quantum foam, this might imply that even the most basic particles exhibit various behaviors in different regions of space-time. The possibility that cosmic rays may convey information about their interactions with quantum foam, perhaps impacted by variations in space-time, is a hypothesis that has been put up by some scientists. Observing these slight changes could reveal information about the foam's properties. If we can understand how cosmic rays change after passing through different regions of space-time, it might offer indirect proof of quantum foam's effects. In the future, with the help of quantum computers, we will be able to model quantum foam and see its properties. Scientists may be able to put hypotheses regarding quantum foam and its function in space-time structure to the test by executing simulations at the most microscopic sizes. We may soon be able to piece together our universe's turbulent beginning as computing power grows. The Big Slurp. The Higgs field collapses. Exploring the concept of the Higgs field collapse, often referred to as the Big Slurp, delves into a potential cosmic catastrophe at the scale of physics itself. The Higgs field is a fundamental aspect of our universe, providing particles with mass. However, some scientists suggest that it might not be in a completely stable state, making it possible, at least in theory, for the entire structure of reality to collapse into a new altered state. This idea connects to the strange possibilities within physics that touch on the foundations of reality, especially as explored in theories of high-energy physics, quantum fields, and the end scenarios of the universe. The Higgs field currently exists in what is known as a metastable state, meaning it's stable for now, but it isn't necessarily in its ultimate lowest energy state. If triggered by a specific event, the Higgs field could collapse into this lower energy state, creating a radical shift in the universe. This transition is often referred to as a false vacuum decay, where space would change fundamentally, no longer supporting matter, forces, or the elements as we know them. In this scenario, the collapse of the Higgs field would begin as a tiny bubble of altered physics, what some have called a death bubble. This bubble would expand at nearly the speed of light, consuming everything in its path and rewriting the fabric of space-time and energy. The entire structure of matter, from atomic particles to galactic systems, would dissolve in this new physics landscape, similar to how water molecules disperse when boiled. The forces that allow atoms to hold together, such as electromagnetism, might not exist in this new state, making it impossible for any recognizable matter to exist. The concept of bubble nucleation plays a key role here. Through quantum tunneling, a process where particles can shift between states by crossing energy barriers without needing the energy to break them, a bubble of new physics could form. Although this possibility is exceedingly rare, quantum mechanics suggests that given enough time, it could eventually happen. Once formed, the bubble would expand outward, unaffected by any barrier, much like an unstoppable wave of physics reconfiguration. One significant factor influencing this process is the mass of the Higgs boson. Discovered in 2012, the Higgs boson is a particle that gives insight into the Higgs field's properties. Its mass helps scientists estimate whether the Higgs field is truly stable. Current data suggests that our universe might be in a precarious balance, neither fully stable nor entirely unstable, hinting at a potential collapse far in the future. This balance has led to a growing interest in understanding the field's stability on cosmic scales, especially in relation to high-energy events like those occurring in particle colliders. If this collapse occurred, the fundamental constants governing our universe could shift. Constants like the speed of light, the Planck constant, or gravitational constant, are values that seem fixed in our universe, giving structure to physics as we know it. But within the Big Slurp's bubble, these values might have entirely different meanings, or no meaning at all. Physical laws are intricately tied to these constants, so any alteration would lead to a physics landscape incompatible with our current understanding. The implications for matter are drastic. Chemistry, the interactions between atoms to form molecules and substances, depends on a stable arrangement of particles. However, if the Higgs field collapsed, particles wouldn't interact as they do now, leading to a reality where atoms wouldn't form. Chemical reactions that sustain life, planets, and stars would cease, resulting in an entirely barren universe. In this altered physics, mass and energy might rearrange, leading to a field where none of the elements or compounds we know could survive. The gravitational forces that govern the structure of galaxies, stars, and planets would also shift. Gravity as we know it might lose its pull, or it could be completely redefined by the new state of the Higgs field. Black holes, for instance, might behave in entirely unfamiliar ways. Instead of being dense points of space-time curvature, they could disintegrate, explode, or morph into objects with unrecognizable properties. Their singularities, the point of infinite density, might dissolve, rendering black holes unrecognizable or irrelevant in this new universe. The Big Slurp's concept resonates with the idea of cosmic inflation, the rapid expansion of the universe right after the Big Bang, which shaped the cosmos into its present form. But while inflation expanded space, a Higgs field collapse would shrink it, pulling spacetime toward a new, compact state. This contrast highlights the symmetry in physics. One event led to a universe full of galaxies, while another could result in one devoid of any recognizable structure. Theories of a true vacuum suggest that our universe might not be the most stable form of reality. If we exist in a false vacuum, we are essentially floating in a fragile balance that could, under the right conditions, fall to a more stable energy level. In a true vacuum state, the energy configuration would be the most stable possible, and the universe would reach a final, permanent configuration. However, reaching this state could erase the current structure of matter, making it incompatible with our existence. Quantum mechanics introduces a sense of probabilistic survival, suggesting that while a false vacuum decay is theoretically possible, it may take billions, trillions, or even more years to occur. However, since this is a quantum event, the collapse could also happen sooner. Although extremely unlikely, scientists acknowledge the possibility of a collapse event occurring spontaneously due to quantum fluctuations, as improbable as that may be within our current cosmic time frame. The potential impact on dark matter, an elusive substance that interacts weakly with the Higgs field, adds another layer of complexity. Dark matter might react unpredictably within the new energy state, either becoming irrelevant or taking on unknown properties. Dark matter's gravitational pull shapes galaxies, so if it behaved differently, the structure of cosmic systems could radically change or disappear altogether. Questions arise about how this might affect hypothetical advanced civilizations. If intelligent life exists elsewhere, it's conceivable that they might have technology advanced enough to detect, or potentially prevent, a vacuum decay event. While speculative, some theorists suggest that a civilization might develop warning systems or tools to detect energy fluctuations, signaling an impending Higgs field collapse. However, given the nature of a death bubble, it's uncertain if any technology could counteract the swift expansion of this new physics state. Beyond theoretical research, some scientists have raised concerns over human experimentation, specifically within high-energy physics labs. Particle accelerators, which reach energy levels similar to those in the early universe, push the Higgs field to its limits, raising questions about whether human-made experiments could spark such an event. While the chances are infinitesimally small, the fact that it's even a remote possibility has led to cautious speculation. The Big Slurp theory tests the boundaries of quantum mechanics and field theory, suggesting that the framework we use to understand particles and fields might need a new approach. Just as the discovery of quantum mechanics transformed classical physics, a false vacuum decay event would reveal limitations in our understanding of fundamental forces and fields, potentially leading to entirely new models for reality. In this view, a Higgs field collapse could act as a reset button, stripping away the complex structures and rules we observe, and reducing everything to a new, simpler form of existence. This process would make it nearly impossible to detect remnants of the previous universe, erasing all markers of our current cosmic history and starting a fresh slate, potentially even leading to a new Big Bang in a separate universe or dimension. Dark energy runaway, the universe torn asunder. Dark energy, the force believed to be behind the accelerating expansion of the universe, has introduced some of the most profound mysteries in modern physics. Its effects extend beyond just pushing galaxies apart. Dark energy has the potential to shape the ultimate fate of the universe. The idea that this force could continue to gain momentum and eventually lead to a dark energy runaway carries with it startling consequences. Unlike the gradual dispersal seen in conventional expansion theories, runaway dark energy suggests a universe that could be torn apart from the largest cosmic structures down to the very atoms themselves. Dark energy, which accounts for around 68% of the universe's energy density, is a form of energy believed to be intrinsic to space itself. Discovered in the late 1990s, dark energy was initially thought to represent a cosmological constant, essentially an unchanging force that would keep space expanding at a steady rate. But as scientists explored further, they found evidence that dark energy's influence might not be static. Instead, it could grow stronger over time, leading to a universe where everything is increasingly pulled apart. The cosmological constant was proposed by Albert Einstein as a term in his equations to allow for a stable, unchanging universe. Yet, as astronomers learned more, they realized the universe was not static, but expanding. The mysterious force that drove this expansion seemed to fit well with the cosmological constant, but what if it isn't so constant after all? If dark energy increases with time, The growth could shift from steady expansion to an uncontrollable runaway acceleration. In this scenario, dark energy would eventually overpower all forces that hold the universe together. One way to imagine this is through the idea of negative pressure. Normally, gravitational forces attract matter, but dark energy exerts a type of negative pressure, a repulsive force that expands space itself. This force is so subtle on a small scale that it has little effect on objects as small as solar systems or galaxies, where gravity remains dominant. But at the cosmic level, dark energy's effect becomes significant. Over time, as space itself expands, dark energy's influence increases. The larger the space, the more dark energy fills it, leading to a feedback loop of accelerating expansion. This process could eventually lead to a scenario known as the Big Rip. In this extreme hypothesis, dark energy's acceleration grows so powerful that it overcomes the fundamental forces holding galaxies, stars, and even atomic particles together. First, it would pull apart galaxy clusters, then the galaxies themselves, followed by individual stars and solar systems. In the final stages, even atoms would be torn apart, as the force of expansion becomes greater than the forces holding particles together. The Big Rip would be the universe's ultimate undoing, breaking down reality at every level. The Big Rip isn't the only possible outcome, however. There's another idea called the heat death, where dark energy continues to expand space but not to a destructive extreme. In this model, the universe cools over time as galaxies drift further apart, leaving behind a dark, cold, and isolated cosmos. Stars would burn out without fresh fuel, and eventually, all that would remain is a thin mist of particles spread across an almost empty space. This outcome, while not as dramatic as the Big Rip, would lead to a dead universe, one where energy is so spread out that no further interactions or life processes could occur. The influence of dark energy on galaxy clusters provides some of the most striking evidence of cosmic acceleration. Galaxy clusters, bound together by gravity, are beginning to experience dark energy's pull. Over billions of years, even the gravitational bonds that hold these clusters together could be overcome, leaving each galaxy to drift alone in the expanding space. This isolation would change our cosmic landscape, as galaxies that once interacted with one another through gravity and collision would no longer be able to do so. The concept of a cosmic event horizon is yet another outcome of dark energy's impact. As the cosmos continues to grow, more and more areas of space will eventually pass beyond the horizon of visible light, rendering them inaccessible even by the speed of light. As dark energy expands space, more and more of the cosmos will pass beyond this horizon and eventually disappear from view. Our observable universe is already quite small in comparison to the entire cosmos, and it will continue to shrink as dark energy speeds up, permanently cutting off our ability to see galaxies in the furthest reaches of space. Why does dark energy seem to dominate precisely in the current epoch? Observations show that dark energy's influence coincides with the scale of the universe we currently inhabit. This raises profound questions about the conditions necessary for life to exist. Some scientists speculate that if dark energy had been stronger or weaker, it might have prevented galaxies from forming, limiting the chances for stars, planets, and life itself to develop. Quantum fluctuations, tiny shifts in energy levels within empty space, could also play a role in dark energy's behavior. On microscopic scales, particles pop in and out of existence, and some theories suggest that this vacuum energy contributes to dark energy. If true, then dark energy may not be a constant force, but instead fluctuates with the quantum state of the universe. This concept brings quantum mechanics and cosmic expansion together, hinting at a deep, still unexplored connection between the smallest and largest scales of existence. The Hubble constant, which measures the universe's rate of expansion, has presented unexpected challenges in understanding dark energy. Different methods of measuring the Hubble constant yield slightly different results, creating a Hubble tension that scientists have yet to resolve. This discrepancy could hint at unknown effects of dark energy, suggesting that it might vary across different regions or evolve in ways we don't yet understand. While dark energy drives expansion, dark matter, another unknown form of matter, acts as a gravitational glue that binds galaxies together. These two components, though fundamentally different, interact in ways that shape cosmic structures. Dark energy pushes galaxies apart, while dark matter holds them together on smaller scales. Their delicate balance determines much of the universe's large-scale structure, making both critical in the cosmic tug-of-war that defines our universe's evolution. Observing distant supernovae or exploding stars has been crucial for measuring dark energy's effects. When astronomers observed these standard candles at great distances, they found that the universe's expansion rate is increasing. This discovery, which led to the 2011 Nobel Prize in Physics, confirmed the presence of dark energy and its accelerating effect, allowing researchers to study its influence over cosmic time. Looking ahead, next-generation telescopes, including the James Webb Space Telescope, will allow astronomers to observe even more distant galaxies and supernovae, refining our understanding of dark energy. As these observatories collect data, they'll help map cosmic expansion with unprecedented accuracy, potentially revealing changes in dark energy's properties over time. Each piece of new data helps refine our models, providing clues about dark energy's true nature and its potential to lead to a dark energy runaway. Dark energy's effects could extend into black hole behavior. While dark energy drives cosmic expansion, black holes pull in matter with immense gravitational force. Over vast timescales, runaway dark energy might alter the growth rates of black holes or even limit their formation. Some theories suggest that black holes could evaporate due to a process known as Hawking radiation, potentially influenced by dark energy's role in expanding space. The relationship between dark energy and the multiverse hypothesis also provides a speculative but intriguing angle. If multiple universes exist, each could have a different level of dark energy, affecting their structure and evolution. In some pocket universes, dark energy could prevent galaxy formation, while in others, it might be weak enough to allow complex cosmic structures like ours to form. The idea of a multiverse raises questions about whether dark energy's presence in our universe is simply a result of cosmic selection. The reverse Big Bang, the cosmic cycle. In a universe that could one day reverse itself, drawing toward a cosmic implosion rather than endless expansion, the physical rules and processes we know may end in a collapse known as the Big Crunch. This theory suggests that after the universe reaches a critical threshold, it may stop expanding, reversing into a contracted state that compresses everything back to a point, an event akin to a Big Bang in reverse. If this were to happen, it would signify a powerful shift in how we understand matter, energy, and the universe's very structure. The contraction process would cause galaxies, stars, and planets to converge as gravity overtakes dark energy, pulling cosmic bodies inward rather than letting them drift further apart. Dark energy, which we currently understand to be the force driving the universe's expansion, would have to either weaken or reverse for the Big Crunch to become a possibility. This points to a deeper mystery. Why is dark energy dominant now, and what might trigger its reversal in the distant future? One key factor in a contracting universe is the role of gravity. In the current expanding universe, gravity works locally to form galaxies, stars, and planetary systems, but it loses out to dark energy on a large scale. However, in a universe where dark energy diminishes, gravity could ultimately dictate the universe's fate. As the expansion slows, galaxies would be drawn closer together, eventually forming dense superclusters. Stars within these galaxies would follow, resulting in increased chances of stellar collisions and supermassive black hole mergers, where entire galaxies collapse into singularities. The cosmic fabric itself would begin bending inwards, with the universe's observable horizon shrinking as vast portions of the cosmos fall out of view. The concept of a cyclical cosmos emerges organically. According to this theory, the Big Crunch isn't the end of the universe. Rather, the collapse starts a new Big Bang. Another round of expansion and contraction might follow this rebirth, implying an endless succession of cosmic life cycles. This theory postulates that these resets are heavily influenced by quantum fluctuations, which are small changes in the quantum field. It is possible that fluctuations, in the extremely compressed condition just before a Big Bang, are the first spark that sends the cosmos back into expansion. Normally, such fluctuations only influence subatomic particles, but in this case, they may determine the beginning of a new universe. Another implication of a cyclic universe is that after each Big Bang, the entropy, the degree of chaos, resets to zero. Systemic disorder and chaos increase as entropy rises with time. In theory, though, the entropy may conceivably go back to zero if the Big Crunch triggers a Big Bang, effectively turning the universe back to its initial condition. This may indicate that the accumulation of disorder from one universe cycle gets cleared away at the beginning of each new cycle. This idea changes our perception of entropy and time by posing the possibility of a cosmos without a final resting place, but rather repeated cycles in which the passage of time may exhibit altered behavior, including resetting or even reversal. In a contracting universe, dark matter's behavior would likely influence how galaxies and other cosmic structures merge and compress. Some theories propose that dark matter could interact with itself in ways we haven't yet observed. This could lead to new phenomena as the universe contracts, with dark matter potentially forming dense structures alongside ordinary matter, affecting the collapse dynamics in ways that challenge our understanding of gravity. As the universe compresses, the laws of physics as we know them may undergo fundamental changes. Some theories in quantum loop cosmology suggest that instead of a violent singularity at the Big Crunch, a smoother bounce could occur, where the universe contracts to a critical point before expanding again. This bounce concept challenges the traditional view of singularities, proposing that rather than an infinite density point, the universe might rebound smoothly. This alternative view offers a different framework for understanding the beginning and end of cosmic cycles, perhaps bypassing the infinitely dense singularities typically associated with Big Bangs and Big Crunches. During the contraction phase, matter as we know it would break down under the intense gravitational pull. Over vast timescales, protons, the building blocks of atoms, might decay, leaving behind only fundamental energy or exotic particles. This decay process would ensure that by the time of the Big Crunch, all complex structures, stars, planets, and even atoms, would have dissolved into their simplest forms, creating a universe ready to reassemble into something new. This eventual contraction hints at a cosmic heartbeat, a rhythm of expansion and contraction that might define the universe's life cycle. Each expansion would allow for galaxies, stars, and possibly life to evolve, while each contraction would bring everything back to a unified point, erasing all evidence of the previous cycle's structure and starting anew. The universe's heartbeat speaks to a possible pattern underlying existence itself, suggesting that each cycle brings about unique conditions, possibly even different physical constants. If constants like the speed of light, gravitational strength, or the fine structure constant, which affects atomic behavior, change with each cycle, then each Big Bang might set the stage for a universe with different physical rules. This idea implies that while certain universes might allow life to develop, others may be radically different, shaping structures and phenomena beyond our current understanding. This view of shifting constants also raises questions about whether life, as we know it, could ever reappear, or if each cycle creates completely alien realities. The fast expansion that followed the Big Bang, known as cosmic inflation, may be better understood if the universe were to contract. A fresh Big Bang may usher in a contraction period that, according to theory, might have a unique type of fast collapse, paving the way for yet another inflationary phase. Given the correlation between the two processes, it's not out of the question that the universe undergoes periodic contractions that prepare it for periods of tremendous expansion. With each cosmic rebirth, inflation might restore large-scale structure, acting as a link between cycles. At the extreme density of a big crunch, quantum gravity effects are expected to dominate. Unlike traditional gravity, quantum gravity combines the principles of quantum mechanics with gravitational forces, a combination only significant at scales like those in black holes or a contracting universe. Quantum gravity might reveal new behaviors at these scales, suggesting that space and time could behave differently as the universe contracts. Some physicists propose that space and time might dissolve entirely, replaced by a new quantum field that births the next universe cycle. The reason that matter predominates over antimatter in our universe is due to baryogenesis, another process that would be impacted by the Big Crunch. Particle interactions may change as a result of the contraction, which may affect the following cycle's matter-antimatter balance. A world where antimatter prevails, offering a reality radically different from our own, might be the result of this transition. Whereas our universe favors matter in this cycle, another cycle might prefer antimatter. Many deep concerns concerning the nature of time are brought up by this cycle of creation and destruction. There is a clear forward motion of time in our universe that is associated with the growth of entropy. But if entropy is reset by the Big Crunch, then the arrow of time may go backwards or even stop, changing how we see the past, present, and future. This perspective on time argues that the universe's chronology is not a straight line, but rather a revolving loop, which questions the idea of linear time. The visible horizon of the universe is becoming smaller as galaxies are getting closer together. The sky would become darker as celestial bodies converge, to the point where even nearby galaxies would have faded from vision. This shrinking horizon illustrates how space itself would compact, confining all matter within a smaller region and giving the universe an almost claustrophobic finality. The cosmic event horizon would mark the limit beyond which we can observe, contracting as the universe tightens, offering an eerie prelude to its final collapse. The universe's cycle could be a grand illusion, a cosmic rhythm where expansion and contraction mask a deeper reality. Each Big Bang and Big Crunch might be just one movement in an endless dance, a strange and enigmatic heartbeat that defines existence. By considering the Big Crunch and a reverse Big Bang, we tap into the profound mysteries of how our universe could end, not in a vast, empty coldness, but in a cosmic rebirth. Strangelets, the universe's strange new flavor. The universe is composed primarily of ordinary matter, protons, neutrons, and electrons, that forms the stars, planets, and galaxies we observe. However, theoretical physics proposes the existence of a more exotic form of matter known as strange matter. This hypothetical substance could potentially alter our understanding of the cosmos, presenting properties that challenge the conventional laws of physics. Strange matter is theorized to consist of strange quarks, in addition to the up and down quarks that make up ordinary matter. In extreme conditions, such as those found in the cores of neutron stars, quarks might not be confined within protons and neutrons, but exist in a free state known as quark matter. If strange quarks are present in sufficient quantities, this matter could become strange quark matter, potentially more stable than ordinary nuclear matter. Small chunks of strange matter, called strangelets, are hypothesized to have the ability to convert ordinary matter into strange matter upon contact. This process raises theoretical concerns about a chain reaction, where strangelets could transform the matter around them, potentially affecting entire planets or stars. However, current scientific understanding deems this scenario highly unlikely, as no experimental evidence has confirmed the existence of strangelets. Strange matter might form in environments with extreme pressure and density. Neutron star collisions and the cores of collapsing stars, supernovae, are possible sites where conditions are sufficient for the creation of strange quark matter. During these cataclysmic events, matter is subjected to forces that could deconfine quarks, allowing them to combine into strange matter. Studying these phenomena could provide insights into the fundamental forces at play in the universe. If strange matter is stable, entire stars could be composed predominantly of it, leading to the existence of strange stars. These stars would be even denser than neutron stars and might exhibit unique characteristics, such as different thermal emissions or rotational behaviors. Detecting strange stars would require careful astronomical observations, possibly involving the analysis of X-ray or gamma-ray emissions that differ from those of known stellar objects. Some theories suggest that strangelets could have formed shortly after the Big Bang during the quark epoch, a time when the universe was filled with a hot, dense plasma of quarks and gluons. If strangelets were created in this primordial environment, they might still exist today as relics, offering clues about the conditions of the early universe. Detecting such particles would be challenging due to their rarity and the vastness of space. The nature of dark matter, which makes up approximately 27% of the universe's mass-energy content, remains one of the biggest mysteries in cosmology. Some scientists have speculated that strangelets could be a component of dark matter due to their non-interaction with light and regular matter except through gravity. However, this hypothesis lacks experimental support, and dark matter is more commonly attributed to weakly interacting massive particles, WIMPs, or other exotic particles predicted by extensions of the standard model of particle physics. In the extreme gravitational environments of black holes, matter is compressed to extraordinary densities. Theoretically, conditions near the event horizon or during black hole mergers might be conducive to the formation of strange matter. If strangelets are produced and ejected during these events, they could disseminate throughout the galaxy. Observations of high-energy cosmic rays and gamma-ray bursts could potentially provide indirect evidence of such processes. The idea that strangelets could catalyze the conversion of ordinary matter into strange matter poses intriguing, albeit speculative, questions about the universe's stability. If such a transformation were possible, it could lead to a gradual shift where stars, planets, and other structures convert into strange matter over astronomical timescales. This scenario is considered unlikely based on current scientific understanding, as it would require conditions and mechanisms not observed in the universe. The properties of strange matter could, in theory, influence cosmic evolution. If strange matter were to become prevalent, it might affect the universe's expansion rate or play a role in phenomena like the Big Crunch, a hypothetical scenario where the universe's expansion reverses, leading to a collapse. Alternatively, strange matter could contribute to conditions favorable for a new Big Bang, initiating another cycle of cosmic evolution. These ideas remain speculative and are topics of interest in theoretical cosmology. Research into strange matter and strangelets pushes the boundaries of particle physics and quantum mechanics. Studying these hypothetical forms of matter could reveal new insights into the strong nuclear force, one of the 4 fundamental forces in nature, which governs how quarks combine to form protons and neutrons. Understanding strange matter could help physicists refine models of atomic nuclei and the behavior of matter under extreme conditions. If strange matter is metastable, it could eventually decay into other forms of matter, potentially releasing vast amounts of energy. Such decay processes might be associated with cosmic events like gamma-ray bursts, the most energetic explosions observed in the universe. Investigating these bursts helps astronomers learn about the life cycles of massive stars and the mechanisms of energy release in extreme astrophysical events. The anthropic principle suggests that the universe's fundamental constants are fine-tuned to allow the existence of life. The scarcity or absence of strange matter in our observable universe might be a factor in this fine-tuning. If strange matter were widespread and capable of converting ordinary matter, the conditions necessary for life as we know it might not exist. Alternatively, it's a subject of speculation whether life forms based on strange matter could arise, possessing biochemistries and physical properties vastly different from terrestrial life. The hypothetical properties of strange matter have led to discussions about potential technological applications. If harnessed, strange matter could offer new energy sources or materials with unique properties. However, The risks associated with manipulating a substance that could potentially transform ordinary matter pose significant ethical and safety considerations. As of now, these ideas remain in the realm of theoretical exploration. The study of strange matter and strangelets invites us to consider possibilities that challenge our current understanding of physics and cosmology. While no experimental evidence has confirmed their existence, researching these concepts expands our knowledge of how matter might behave under extreme conditions. It encourages the development of more comprehensive theories that could unify quantum mechanics with astrophysical observations. Advancements in particle physics experiments, such as those conducted with particle accelerators and astrophysical observations using advanced telescopes, may one day provide data to support or refute the existence of strange matter. Until then, strange matter remains a fascinating topic that exemplifies the ongoing human quest to unravel the mysteries of the universe. The edges of the universe are not merely boundaries, but thresholds to realms where the familiar laws of physics dissolve into a sea of strangeness and wonder. As we venture into these uncharted territories, we are confronted with the profound realization that the cosmos is far more complex and enigmatic than we ever imagined. Feel free to subscribe if you enjoyed the video. Thanks for watching.